That I don't know. वो अपने को पता नहीं चलेगा क्योंकि हम लोग PhD स्टूडेंट्स अच्छे PhD स्टूडेंट्स मिलते हैं तो उसके लिए अभी स्टेट
Good morning to all. I welcome you all to the day 5 sessions of VLSI design. So I welcome you all for the day 5 session of VLSI design. Our expert Dr. Anand Bulushu is here with us. Dr. Anand Bulushu is presently working in Electronics and Communication Engineering Department of IIT Roorkee. He also worked as Senior Research Engineer with IIT Bombay and as Senior Design Engineer with Freescale Semiconductor India. Dr. Bulushu has done his doctoral in Microelectronics from IIT Bombay. He is handling DST projects related to nanoscale VLSI circuit design. He is member of IEEE Circuits and Systems Society, Electron Device Society and Solid State Circuit Society. His area of interests are circuit design, variation-aware VLSI circuit design methodology, delay models, delay and timing models for VLSI circuit, VLSI devices, novel device circuit co-design methodologies. He has number of publications in IEEE Transaction and other reputed journals. So I welcome you, sir, and I invite you for your talk. Welcome, sir.
Good morning. So today I'll talk about mainly there are several multi-gate transistors which are being proposed these days, and these are all, and one of them, FinFETs, has actually gone into production. It is already in production these days, and Intel, many of its some of its new microprocessors are in FinFET technology, which is a multi-gate technology, and several other companies are actually coming up with FinFET technologies, and FinFET is now almost mainstream for high performance processor design. So, but there are, as with any new technology, there are several issues associated with it, and we'll mainly discuss the issues associated with this. So, what I will do is, first I will discuss why these multi-gate devices came. I will discuss only regarding FinFETs as an example, and then what is the basic operation of FinFET devices, how and what are the issues related to FinFET, circuit design issues related to FinFET devices. Then I will talk about work of our group, So what is our simulation setup, and how does our group, what are our group's findings, and regarding the issues with FinFET circuit design and their solution. So we know that this is an law of it's a statement of from economics study of markets. Actually, it's not a technical statement, So something called Moore's law. So what it says is that it's a very old. The Gordon Moore, actually, he is one of the founders of Intel. He studied that there is a trend to increase in the number of components per function. I mean, how can how the scaling happens, how markets are driven. There is a linear trend in that, and that is what prompted. That was the that was the motivation behind, economic motivation behind scaling. Then Dennard proposed a method of scaling, and which we call constant field scaling, and that constant field scaling actually became the basis of entire scaling. But that is now under strain. The constant field scaling was no longer possible as the supply voltage is dropped to around 1.5 volt or 1 volt, because below that the supply voltages came to be very close to threshold voltage, and you might be knowing what is threshold voltage of a MOSFET, etc. So the supply voltages came to being very close to threshold voltage, and therefore it was no longer possible to bring down supply voltages. So technology scaling as we know it started facing a lot of issues, and there are new solutions which are being suggested, and multi-gate transistors or FinFETs or tri-gate transistors. So FinFET and tri-gate transistor are very closely, their structures are very closely related to each other, and their physics is almost the same. So FinFET and tri-gate transistors, I put them in one category. So these FinFETs are the main multi-gate transistors which are coming into market now. So what are the issues? We know that, see, this is what we want is, this is a conventional MOSFET. What we want is the gate should control the channel here. So there is a channel here which is formed when the gate voltage, this is an N MOSFET suppose. So when the gate voltage is taken high, the channel is formed here connecting source and drain, and gate should control the channel. So what happens is when gate voltage is increased, there is an N-type, there is a negatively charged depletion region which is formed here, and when gate voltage is further increased, an inversion charge is formed here. Okay, so this depletion charge is also formed because of the drain. That is, there when the drain voltage is high. See, when the drain voltage is high and source voltage is low, only then the current would flow from drain to source, isn't? If there is a connecting inversion channel. Okay, so when the drain voltage is high, you also have, see, this is in an N channel MOSFET, drain is N type and this substrate is P type. So there is also a depletion region between, reverse bias depletion region between the drain and substrate, isn't? So that depletion region, and there is a depletion region associated with the gate. So these two, the drain's depletion region starts affecting the, starts taking a large part of the gate's depletion region in some sense. So there is a, so the gate voltage has to be supported by, see, gate is a, you have given a high voltage to the gate. So gate voltage has to be supported by negative charges, or positive charges in the gate have to be supported by negative charges in the channel connecting the drain and source. It's channel connecting the drain and source, isn't? So now these negative charges are depletion charges and inversion charges. So, and some of the depletion charges are because of the drain to body reverse bias junction. So the depletion charges which support the gate's positive charges are now being eaten up by the drain's depletion region, isn't? Drain to body depletion region. So the gate's positive charges have to be now supported by more number of negative charges in the channel. which are inversion charges. So what happens is, inadvertently, because of the drain voltage, the threshold voltage starts dropping. So when you increase the drain voltage, the threshold voltage is lower, and when you have a smaller drain voltage, essentially the threshold voltage is higher. So if the threshold voltage is lower, there are two issues. One issue is that, main issue is that, if the threshold voltage is lower, leakage currents are high, because leakage current, which is an off state current, so if it is exponentially related to threshold voltage, that is, if threshold voltage reduces, exponentially the leakage current increases. So that's why you don't want a minor change in threshold voltage also, because a minor change would lead to a large change in the leakage current, large increase in the leakage current, and you want this to be a good switch, the MOSFET, isn't? So if the leakage current is high, it's not a good switch. So that is the issue. So that's what. So one problem is drain induced barrier lowering, which is roughly what I was saying. From a top view, what we would, from a very fundamentally, what we would say is that the drain voltage, when it is high, it starts controlling the depletion region and potential in the channel. If drain voltage is taken high, the potential in the channel gets affected. Okay, it also becomes high. So since it becomes high, since the inversion charge is now affected. Okay, inversion charge has to the inversion charge has to increase, or the drain starts controlling the inversion charge, which we don't want. We want gate to control the inversion charge and not drain, isn't? So this is one issue. So the other issue is, since once the drain starts controlling the inversion charge, threshold voltage drops and subthreshold leakage current increases exponentially. Then there is another issue, which is when the gate is off, when the gate voltage is 0 and drain voltage is high, there is a leakage mechanism which sets in here at the gate, at the channel, drain, gate, the region where all the three meet each other. So, and that also leads to another leakage current, which we call gate induced leakage current. Then with technology scaling, we are reducing the oxide thickness, so that increases the tunneling currents. So there could be a gate oxide tunneling current, and to avoid gate oxide tunneling current, the solution that people are taking, that industry is taking, is that no reduction in oxide thickness should be done. So that is the solution that industry had taken. Or they are also taking another solution, which is high K metal gate. So they will put instead of a thin oxide layer here, they will put a high permittivity thick dielectric layer instead of the. So this is the gate oxide. So instead of that, they put a thick high permittivity dielectric. So that equivalently is like a thin gate oxide. So these are all different solutions that people are proposing in planar MOSFET, but the planar, all these solutions have, so to continue scaling, to continue technology scaling, all these solutions don't work. So broadly, what is this technology scaling? You reduce the channel length. So where is the channel length in this? Is it visible? Dikh raha hai, no? Right. So that is the distance between the source and drain. This distance is the channel length. You reduce the oxide thickness, you increase the doping density here, and you reduce the depth of drain and depth of source. So several dimensions, doping densities are all reduced. So that is essentially what happens in technology scaling, that increases speed of circuits. Okay, and without increasing, ideally without increasing the power density, that is power consumed per unit area on the chip. So that is basically technology scaling, and this is what had driven VLSI industry for several decades, around 40 years. But now technology scaling is almost becoming an impossible act, though manufacturing people are finding out methods to continue with technology scaling, but it's almost becoming an impossible act now. And that is why the VLSI industry is now coming up with newer transistors, and main new candidate is FinFET, which is a multi-gate transistor or double gate transistor essentially. So how did it all progress? One could see that this is the bulk planar silicon, bulk silicon planar MOSFET, and then it has a, there is some disturbance which is coming in. Dekho. Achha. Yeah. So then it evolved as silicon on oxide. So what happens here is the silicon film is reduced. That is, this is just the gate. Then there is a silicon film, and there is an oxide below silicon film again, and so the in bulk silicon, the entire transistor is formed here on a bulk full silicon wafer, in some sense. Okay, here the main substrate of the silicon wafer in SOI, and in SOI what happens is the area where the transistor is formed, the top part of the silicon and the bottom part of the silicon, which is mechanical support of the wafer, are separated by an oxide. So that reduces capacitances and thereby increases speed of circuits. Then the third, another evolution took place where people proposed that let us keep a gate below here, because the gate control is reducing. Gate's control is reducing over the channel, and it is the drain's control which is increasing. So let us strengthen the gate in some sense and put two gates, one above and one below, and both should be shorted. So that's how the gate control over the channel increases. That was the third idea. So in SOI, below the bottom oxide, keep another gate. That was the idea. Okay. And then they realized that it's very hard to manufacture this kind of thing. So they said that this SOI or bulk, what we do is we etch it further, form a silicon like this on this silicon on oxide. See, this is oxide. This black part is oxide. Above it is silicon. Below it is black part is oxide. Below you have silicon. Above you have again silicon. So etch this silicon further and form a small block of silicon. Over it form oxide, and over that form the gate. So now you have double gate. One from this is silicon. One from this side. One from this side. So this double gate structure is flipped by 90 degree in some sense. This double gate structure is flipped by 90 degree in some sense. So there is this gate, and in between you have silicon. Okay. So then it started evolving further, and the idea now is gate all around. So you have silicon in between, oxide all around it, and the gate all around that. So that is this is where now researchers are focusing on. So let us again look at the thing. So how does this FinFET device look like? So you have bulk silicon here, buried oxide, there is an oxide there, it's the SOI FinFET, and you have silicon here. This green part is silicon. Okay. Over that you have oxide. Under this green part is silicon. This is oxide. Okay. So this yellow is silicon. So it is going from here till here. It's going beneath, under this structure, isn't it? As you can see. And above that you have oxide. Okay, silicon dioxide, and above that you have gate formed. So this is the structure of the FinFET device. Okay, so this is, where is the source and drain? It's not. Where is this? This is source and this is drain. So source and drain, I mean these two are interchangeable. Source and drain depends on what has higher potential. So these are source and drain, and these are connected through this. See, this source continues till here and drain continues till here. So this is source pad. This is contact for the source. This is contact for the drain. Okay. So the source so contact is made here over the source pad, and source continues till here. Drain, the contact is made here, drain continues till here. So this is called source pad, this is called source extension region. This is called drain pad, and this is called drains extension region. And these two are getting connected beneath under this structure through the same silicon. Okay, and above it you have oxide, above that you have gate. So this is the gate. So where is the channel formed now? Channel is formed under this structure. So here you have increased the gate oxide thickness. So this is not part of transistor, it's just electrical connection between the two gates. So when you increase the oxide thickness, threshold voltage increases, isn't it? So this part you have increased the oxide thickness so much. Here you have increased the oxide thickness so much that the gate is not controlling the channel here. This part of gate doesn't control the channel. Here you have thinner oxide. So this part of gate actually controls the channel because there is silicon under this, isn't it? You can see. It's like a bridge being formed over a road of silicon. You can take it that way, isn't it? So now, like it is here the same way symmetrically on the opposite face, which we are not able to see in the figure. So here you have thin oxide, gate and silicon. Okay, likewise on the other side. So it's a double gate. It's coming from both the sides, the silicon. So it's as if it is this one, if you can see. So here you have a thick oxide, but here you have a thin oxide. Here again you have a thin oxide. So it's like gate on both the sides. It's silicon. Gate is the oxide is formed on both the sides. Here you have thick oxide. So forget about that part, top part. So gate here, thin oxide, and fin here. So now this gate and this gate are electrically shorted from top. You can see from the top they are electrically shorted. So these two gates would control the channel inside the film. When the gate voltage is high, a channel is formed. If it's an N-type MOSFET, and when the gate voltage is low, the channel is not formed within the fin. Is that fine? So that is what is happening. This is the top view. You cut it from here and look from the top. So how does it look like? Drain, this drain, source, this source pad. Then you have these extension regions. This source extension. So this is the source extension. This drain extension. This is the drain extension. And this is what is the channel part under the gate. Okay. So here you have one gate. Here you have another gate. And this is the channel part. Is that fine? So these are images you can see. So for example, this is the fin and you have gate all around, gate formed over it, and there is a thin oxide here. You can see. So this is a tri-gate FinFET. Top oxide is also not thin, not thick. It is thin here. So Intel uses a tri-gate structure. Others use a double gate structure. Like we are going to discuss a double gate structure where the top gate is disabled by thickening the oxide. Okay. So how does the electron density look like? The first part is a kind of introduction. After that, I'll talk about our group's work. So you people can discuss in between if you want. But I think the format is that the discussion is done after the entire thing is delivered. So here what you can see is okay. So what is the silicon film thickness? So this thickness, this is height of the film, okay, and this is the thickness of the fin. That is, thickness of fin is this. Can you see? This from one gate edge to the other gate edge. That is thickness of the fin, T fin, and height of fin. So height of fin is essentially the width of the device in some sense. So the gate, this is fin, the gate is formed here and here. So height of the fin is width of the device. What is the width of device now? Height of fin plus height of fin. So double the height of fin is width of the device. Length of the device is, suppose gate is formed for this much part, then this is the length of the device from here till here. Because this is source coming till here, this is drain coming till here. So length is this, and height is the width. So double the height is the width of the device. Because top is anyway we are neglecting because we are increasing the oxide thickness there. The top is gone from the thing. So this is height plus the other side's height. That makes the width of the device. So this is silicon film thickness. Where does the cursor go? This is the silicon film thickness, isn't it? So, or film thickness, you can see here, or fin, as we call it, fin thickness. So this is with respect to the fin thickness. How does the electron density vary when you increase the for a large gate voltage, that is above threshold gate voltage? So now you have an above threshold gate voltage, and how does the electron density vary? So one can see that the electron for very small fin thickness, let us forget about it. That is quantum dominated, and even now I think industry is not ready to go there. It is all still in research. Okay. So let us look at these moderate values of fin thickness.
We are not getting the video.
Let us look at these moderate values of fin thickness. So this is a moderate value around 10 nanometer. So if it is 10 nanometer, then you can see that when the gate voltage is high, when the gate voltage is high, the electron density is almost uniform throughout the fin. What is this? This is throughout this fin, from here till here. Okay, in dono ke beech mein. Did you understand? Between the two gates. So between those two gates, the electron density is almost uniform. Okay. So near the, so this is one edge of the, this is one silicon film, silicon oxide interface. This is another silicon oxide interface. That is, this is the gate, isn't it? You have one silicon oxide interface here. The other silicon oxide interface is here, and this is bulk silicon. Okay. There is no interface. It's a uniform material. So what happens is electron or hole scattering is highly affected by the interface. Near the interface, scattering is high. Okay, and in the bulk, within the bulk, scattering is low relatively. So mobility is, if the electrons are all present near the interface, mobilities are low. If they are present, if several of them are present within the bulk, average mobility is high. Okay, so for around 10 nanometer, what we are seeing is these two are gates. This is 10 nanometer film, a fin. So electron density is high throughout. So electrons would flow in all the parts. So in the bulk, they would have a high mobility. So you have, where is it? You have a relatively high mobility for around 10 nanometer. So after that, when you increase the fin thickness, that is when you increase this fin thickness, okay, what you find is that because the electric field is not high throughout, you know, when you increase the fin thickness, you can see that the electric field in the gates control over the middle parts would reduce. When you increase the fin thickness, the gates control over the middle part would reduce. It would remain only at the near the interfaces. When the fin thickness is small, fin is small, thin, then the gates control over the entire fin would be high. That's why you have high electron density, the high electron density throughout. Is that fine? But when you increase the fin thickness, the gates control would remain only at the interfaces. In the middle part, gates control would be low. That's why the electron density is high at the interfaces, and in the middle part it's getting low. So for 20 nanometer, you can see it's even more like that. So what is now happening? The middle part gives a higher mobility because there is no interface there. So average mobility keeps on reducing as you increase the, it will reduce as you increase the fin thickness. The average mobility is best here. Is that fine? Because here it is mostly bulk conduction. It's not interface conduction, interface inversion. The inversion is there throughout the device. Is that fine? So that's why you have perhaps there is a optimum silicon film thickness also. But when you increase the increase the fin thickness, drains control also increases, average mobility also reduces. So short channel effects, I mean that increase in leakage current with drain voltage, that exponential kind of increase in leakage current with drain voltage, those kind of effects which we were discussing earlier also start dominating when you have a thicker fin. And when you have a thicker fin, you have this problem of lower mobilities also. So you want a thin silicon fin, and when you make it thinner than a certain value, quantum effects start dominating. So that is an area of research even now. So now the idea is that keep it near 8 nanometer to 12 nanometer range. So then you get higher mobilities, relatively lower control of drain over the channel. Okay. So this is what we have again. This is another. Um, this is the same idea again discussed. Okay. So what happens to the? So what happens to the threshold voltage? So as I had said, as you keep on increasing the thickness of the silicon film, the threshold voltage, the basic threshold voltage also starts. I mean, no, I'm not talking about the drain controlled, drain induced or short channel effects, drains control over channel and those things, but the threshold voltage also keeps on increasing, because in some sense you can see that gates control over the fin reduces, and therefore the threshold voltage increases, and you don't want a high threshold voltage, otherwise you cannot go for a lower power supply voltage. Okay. So recently what people FinFETs are already coming in industry, so these are the examples of that, and all the main foundries are now giving a FinFET technology option at 14 nanometer, 14 nanometer node, especially everyone is coming up with a FinFET option. It's only FinFET option. Planar option is not available. So now I'll discuss one of the main FinFET structures which was proposed, which is an underlap FinFET, and all the FinFET structures are mostly underlap kind of structures now. So what is visible there? Is this also visible, or only the slides are visible? Only slides are visible in the remote locations. Okay. So okay. So this is the top view of the FinFET structure that we had discussed, isn't? So this is what we had begun with. So here, if the source and drain doping densities are high, one of the major issues with modern day planar MOSFETs or any MOSFET is that you don't want a high doping density in the channel. So cursor is somehow giving an issue, isn't it? Right. So within the channel, you don't want a high doping density here, because if you have a high doping density within the channel, the control. See, what happens is this is a very thin region. Suppose it is 14 nanometer length and 10 nanometer thickness. Okay, so that is around what is the area. This is top view of the FinFET. I think you can relate that point, isn't? This is top view of the FinFET. So where does the cursor go? If you can change the mouse or something. हाँ, because वो cursor के बिना समझ में आता नहीं है where to point, and then no one would understand where am I pointing. Yeah. Highlighter, no. Arrow is the option right now. Is the option creating an issue? Perhaps. Let me try. No one can see, isn't it? No. Is it visible now? Take care. But it goes away sometimes. Right. So this is the top view of the FinFET. I think that one can relate to, isn't it now? So in this top view, one can if the doping, what is the area of this? Let us see. So this is around say 14 nanometer, and this is length is 14 nanometer. Thickness of fin is say 10 nanometer. So 140 nanometer square is the area. Suppose the doping density is 10 to the power 18 per centimeter cube, which is almost the highest allowed doping density. Then how many dopant ions would be present within this? So it's around 140 into 10 to the power minus 14 centimeter cube, the area, isn't? It's a height of the fin is 25 nanometer, which is the typical height. So into 25, so that would make it 2500 plus around 2600 2600 into 10 to the power minus 21 centimeter cube, that is 2.6 into 10 to the power minus 18 centimeter cube. So and you had around 10 to the power 18 per centimeter cube of doping density. So how many dopant ions would be there within this entire silicon fin under the gate? So this is gate, isn't it? This is extension region. These two are extension regions. This is source extension. This is drain extension. This is the only part of fin under the gate. These two are the gates. This is gate, gate, gate oxide, extension region, extension region. Is that fine? Source pad, drain pad. Are you able to relate to what we had seen, the 3D structure that we had seen earlier? I think that is important. So this is the 3D structure. So source pad, drain pad, drain extension, source extension. This is the gate. Is that fine? And the same thing I am showing here. This is the gate, gate oxide, source extension, drain extension, the main channel. So I am saying that the main channel's volume is so small that there are it is around 2.5 into 10 to the power minus 18 centimeter cube, and dopant ions are dopant density is around 10 to the power 18 per centimeter cube. Then you have around 3-4 dopant ions within the channel. Okay. So if there were 1000 dopant ions within the channel, a variation. See, this is a random. The dopant ions come into any silicon are doped. The doping and annealing, doping, ion implantation, annealing, all these lead to a statistical distribution of dopant ions within silicon. So statistical distribution makes sense only if the numbers are large. If there are 1000 dopant ions within the channel, then you can say that okay, it will almost be always around 1000. It could vary from 995 to 1005. But here, if you are having 4 dopant atoms or 3 dopant atoms within the channel, then it could be even 0, it could be even 8 or 10, isn't? So the doping density doesn't make much sense now. So it's better because then you don't know what is the threshold voltage of the device. For what value of gate voltage would the device turn on or off? It's very hard to say now with these kind of dopant, with these small dimensions. So the idea is now don't dope the keep the channel region almost intrinsic. That's one thing. Okay. The other thing is the other idea is that keep the channel region almost intrinsic for another reason. Dopant ions also increase the scattering and reduce mobility. Okay, scattering probability and thereby reduce mobility of the carrier. So anyway, dopants are not contributing much to the device quality. They are increasing variability of threshold voltage by a very large value, unacceptable value, and they are also reducing the mobility. So why not do away with doping? Keep this channel almost intrinsic, so that the mobility is also high, and this variability in threshold voltage, this issue is also handled properly. So that is the basic idea. So that's why this is kept almost undoped. But if you are to keep this almost undoped, then this is the source pad and drain pads. The source and drain pads need to be highly doped, because you need to form ohmic contacts over them. Contact is formed here and here, and contact cannot be formed in a low doped or intrinsic silicon. There you don't form ohmic contact, you form Schottky contacts. So to form an ohmic contact, it's necessary that the doping density be high. So, and also to reduce the resistance. See, now the carrier has to move from here till the gate. The resistance also has to be low, isn't, to keep the resist. These are not gate controlled regions. This is not a gate controlled region. So here, because of the gate voltage becoming high, there is no increase in carrier density. The carrier densities are low here if you keep them undoped, isn't? So you want to, you need to have high doping in the source and drain pad, but the channel has to be very low doped. Okay. So that can be achieved by keeping a low, because the, see, the carrier, the doping density cannot abruptly change here. It would change gradually. It would be a Gaussian kind of distribution. So the doping density is high in source and drain pads. It's very low in the channel, almost undoped. So it gradually changes from very high value, around 10 to the power 20 per centimeter cube, to around 10 to the power 15 per, see, within the channel it's around 10 to the power 15 or 14 per centimeter cube. Here in the drain pad and source pad, it's around 10 to the power 20 per centimeter cube. So it has to reduce by orders of magnitude within this extension region, the doping density, isn't? It has to reduce by orders of magnitude. So when it reduces by orders of magnitude, it becomes very small here at the edge. So near the edge, even within the extension region, the doping densities are very low. Okay, doping densities are very low near the edge, even within the extension region. So most of the FinFETs realized in this manner are underlap FinFETs. They can be classified as underlap FinFETs in the sense that you have low doped regions even within the extension near the channel. So what you find is, for zero gate voltage, this is the electron density. For this is, see, this is the edge of gate. This edge of gate is this and this dotted line. So here you have low electron density, and you can see you have low electron density even near the edge. Outside the gate, outside the channel, even within the extension region, in the near regions, you have low electron density. You can see, isn't? So that's because the doping density here and here is low. Okay. When you increase the gate voltage, you find that the electron density increases in the channel and also in the extension regions. How does it increase within extension region near the channel? Through the fringing electric fields. So gate to extension region, fringing electric fields set in. Okay. See, here the doping density is low. So this is also gate controlled to an extent. See, it's not, the electron density is not as low in the extension region as it is in the channel. In the channel it is very low. Okay. But in the extension region it is relatively quite high. But even then, when you increase the gate voltage, you can see that the extension region electron density is also increasing, not only the channel region. Okay. So this is what happens in all the FinFET structures of this kind. This is underlap FinFET structure, and in my opinion, this is the FinFET structure which solves the scaling issues. But it has this problem that within the extension region also the carrier density is highly modulated by gate voltage. So it's not only in the channel but also in the extension region near the channel, the carrier density is highly modulated by gate voltage. This issue is also there in all these underlap FinFET devices. Okay, but industry perhaps is using a different kind of FinFET device. That's what I guess from reading the literature available from industry. What I feel is that they are perhaps using a highly doped extension region, and it's overlapped. The that is the actual gate length is smaller than the drawn gate length, and the doping is high even within the channel to an extent. The undoped part of the channel is very short. That's what I feel. That's what perhaps industry is doing. Okay. So I will now briefly start discussing what are the issues in and challenges in FinFET circuit design. One of the main issues is width quantization. So as you know, in planar devices, these planar devices, if you want to increase the current, what would you do? You would increase the width. This is the width from here till here. Then this is the width. Then you increase the width of the device. Isn't? Is that fine? That makes sense, isn't it? Okay. So, but in FinFETs, what can you do? Can you increase the width of device? What is the width of device here? Again, the cursor has gone somewhere. What is the width of device here? This height is the width of device. You cannot increase the height. Height is defined by the process technology. Okay. You cannot increase the height. So, to increase width of the device, you need to have another parallel fin. You need to have a parallel fin to it. Okay. So, and the length is fixed. So, width is height, twice the height from one from this side and one from this side. Twice the height is the width of the device. So, if to increase the width, you need to keep another fin there beside it, isn't? Between the two, between the same source drain pads, isn't? So, you can increase the width in quantas. Okay. So, you can increase the width in quantas. See, like this. So, here you have one fin, second fin, third fin, fourth fin, all between the same source drain pad, source pad, drain pad. Is that fine? This is an inverter. If you can. Full screen नहीं हुआ है क्या? Is it? I mean, are you able to see the thing? So this is the. These are all the parallel fins. This is an inverter. As you can see, this is P fin, P FinFET. This is N FinFET. So there are two parallel fins here, and four parallel fins have been shown here, isn't? Okay. So to increase the width, what you had to do, you had to keep parallel fins there. You had to keep. So it works in discrete numbers. You cannot increase the width in a way you want. So this is a major change in circuit design. So one has to think about the circuit design in another manner. So that is, if you want to suppose equate PN ratios, for example, that is a very classical first thing that a classroom student also does, isn't equating PN ratios, P drive and N drive, so that the output transitions of an inverter are rising and falling transitions have equal time, isn't these kind of things? If you want to do, it's very hard to do in a FinFET technology, because there it works only in discrete numbers, isn't it's very hard to achieve that equalities, the exact amount of drive that you want. It's very hard to achieve. So we must start working with these discrete numbers, and that leads to different kinds of CAD tools and for circuit design, and it also leads to a major issue in leakage. See, what happens is, if you increase the width of a device in planar devices, these days the variability of threshold voltage is a major issue. Why? Earlier, suppose you had 2.5 volt supply voltage, and the threshold voltage was suppose 0.5 volts, around 0.5 volts. The difference between supply voltage and threshold voltage, VDD minus VTH, was around 2 volts, isn't? And that defines the on current, isn't? Or that roughly defines the drive current. But now the supply voltage is around 0.9 or 0.7 volts. Threshold voltage is not going below 0.2 volts. So the difference between supply voltage and threshold voltage, VDD minus VTH, is quite small now. So any minor change in threshold voltage actually changes the delay in a major way, because delay is defined by VDD minus VTH. Okay. So delay is changed in a major way. And if VTH changes in a minor way, we also know that leakage current is exponentially changed. So leakage performance of performance is leakage power is increased by a major way if for a minor reduction in threshold voltage, isn't? So minor changes in threshold voltage these days lead to very large variations in leakage and almost unacceptable leakage changes even in the speed performance, isn't? So that the entire design becomes unpredictable. So what happens to this threshold voltage variation? So what we find in a planar technology is that as you increase the width, variation reduces. Why? The variation is mostly because of random dopant fluctuations. As we had seen, the number of dopant ions within a small region of silicon, even for high doping, is very small. The minor change, I mean, there are around 8, 10, 15 dopant ions with which you are dealing. 15 can become 12 very easily, isn't? So that minor changes in dopant ion distribution also lead to a large change in threshold voltage, isn't? So that leads to a large change in threshold voltage. So if the area covered is larger, then the number of, suppose the dopant ions are 30. In a larger, so if you increase the width of a planar device, think of a planar device. If you increase the width of a planar device, under the gate, the silicon area is larger, no? Volume is larger. So in a larger volume, suppose instead of 15 dopant ions, you had 30 dopant ions. Variation in due to statistical variation, the variability in threshold voltage would reduce, isn't? So as you increase the width of a device in a planar device, the variability in threshold voltage reduces. Is that fine? But here in FinFETs, that doesn't happen because as Sapatnekar and his colleagues, this is Sapatnekar's paper, Sapatnekar and his PhD student perhaps. So as those people reported, what happens is that when you increase the number of fins, see, it's not like reducing when increasing the width of device. When you increase the width of device, the entire volume covered is now larger. So number of dopant ions increase, and thereby statistical variation reduces. Now it is discrete, isn't? One fin, second fin. So in this fin, whatever is there are 15 dopant ions. Here you have another. Suppose here you have within this fin 10 dopant ions. You are supposed to have, and here you are supposed to again have 10 dopant ions. So then the variability will be, statistical variation would be large in this as well as in this, could be large, isn't? If these two were the same volume, then it becomes 20 and the statistical variability thereby reduces. But now these two are separate. So therefore the statistical variability stays the same. So therefore the variability of threshold voltage is very high in FinFET technologies because of width quantization. Okay, and thereby the increase in variability in subthreshold leakage, that is off-state power of the FinFET circuits, and the variability in delay performance are all quite large because of random dopant fluctuations in FinFET technologies. That is what Sapatnekar and his group had shown. So this is, I mean, width quantization gives rise to these two issues. One is the entire circuit design methodology needs to take into consideration this discrete, playing with this discrete numbers. We are used to playing with continuous widths, but now we have to adjust to playing with discrete numbers. Already, because of fingers in a layout, we have some idea of working with discrete numbers in a layout. Even in planar technologies, those of you who are working in SEL can see that you might have seen layouts. You see that it's all fingered, isn't? So there you again work with discrete numbers in some sense, but it's not. It's by your choice. It's not by force. But in FinFETs, it's by force. You have to work with discrete numbers. Okay, right. So that is one way, issue. The other issue is leakage. Leakage is highly affected by this width quantization. So the other major issue with FinFETs is the parasitic effects. As you can see, this is okay. I have not written the source here. This is from a Kaushik. This figure is from Kaushik Roy's paper, so I must acknowledge him, acknowledge their group. So here you have this source pad, drain pad, okay, extension region connecting the. This is the channel. So this is gate oxide. Why it is gate oxide here? Okay. So what all and this is spacers. What is the spacer? As you can see here, you have oxide. Here also you have oxide, isn't? This we call spacer. Okay. This is source pad, drain pad. 3D में देखें. So here you have source pad, extension region, oxide, but this is not unfilled. You cannot leave it unfilled. There would be some dielectric here. Okay, that is again oxide or silicon nitride, whatever. So there is some dielectric there. Yeah. So here you have, right. So here you have the channel, gate oxide, extension region. So the extension region offers a resistance. So there is a resistance between source pad and the channel. Okay. Likewise, a resistance here. Okay. And there is a, now between the gate and this extension region, there is this, if you increase the gate voltage, there would be fringing electric fields. So if you increase the gate voltage, there would be an increase in the positive charges on the gate, and gate is a metal. So all the positive charges would get collected at the edges, not within the metal. So never charges get collected within a metal. They all get collected at the edges, isn't? And these charges, positive charges, would get associated with negative charges in the extension region also. They would get associated with negative charges in the channel. They are the inversion charges, inversion electrons. Okay, they would also get associated with negative charges in the extension region through fringing electric fields. Here, the positive charges in the gate would get associated with the negative electrons in the channel through electric field, and here you would have fringing electric field. So that also gives rise to a capacitance. And so there is a parasitic capacitance here. Likewise, there is another parasitic capacitance here. Okay, and the gate also has a resistance. Gate also has a resistance. Suppose there are several fins, and the gate goes like this, connecting all the fins. Then the gate also has a resistance. So there are the parasitics of a FinFET look like this. Extension region is almost as long as the channel region. So therefore, the extension parasitic resistance is quite high. So the parasitic resistance and parasitic capacitance of extension are quite large in a FinFET technology, and therefore the gate to drain coupling capacitance is quite large, and the large value of gate to drain coupling capacitance is a major issue in FinFET circuit design, and also the large resistance of the drain and source extension region. So these are kind of parasitic effects with which traditionally circuit designers are not used to in planar technologies. So here these are major circuit design issues, and they must be taken into consideration at the layout and circuit design levels itself. So now I will discuss our work. Our work is mostly regarding the parasitic effects of taking the parasitic effects of extension region into circuit design. So our work is mostly concerned with this aspect. So I will start with our work. So I think only 15 minutes are left. How much? So I'll talk for about 5 minutes more, and then I'll open it for a discussion. So I think most of the there might be an issue because most of the talks till now might not have focused on a device kind of area. I think this is the first or second talk talking about devices, isn't? Yeah. There might be an issue because of that, but that's why I have not gone into our work and all that right now. I have been trying to discuss the general things. That is the reason. So let us see so how it comes up. Yeah. Where should I start? So this is the top view of the FinFET as we have seen. So this is the main channel, extension, source, drain extension, drain, gate, thin oxide here, thin dielectric here on both the sides, and the thick dielectric. This is spacer. Okay. As you can see in this underlap FinFET, this is the electron density, E density. This is edges of the gate. What are the edges of gate here? These are the edges of gate. This one and this one. This one and this one. So when you cut along this line, you connected line from source to drain, and along that see the electron density. So this is the electron density. You can see the electron density is for low gate voltage, 0.2 volt gate voltage. It is like this. When you increase the gate voltage, it increases here, and also it increases in the extension region near the gate, that is this part and this part. It also increases here, as I had discussed earlier. So it increases within the extension region also. Okay, so there is now a kind of so what you can see is that the extension region's electron density also is changed by a large value. So it is changed by around 2 orders of magnitude, if you can see here, when the gate voltage goes from 0.2 volts to 0.6 volts, isn't? So that's a large change in the extension region's electron density. That leads to a large change in the resistance of the extension region. It also leads to a large change in the gate to extension region capacitance. So now there is a fringing field capacitance from gate to the drain extension region here, isn't? So as you can see, from the gate to the drains extension region, there is a fringing field capacitance, isn't? So for that, a positive charge here in the gate has to be supported by a negative charge within the fin in the extension drains extension region, isn't? So that would depend on what? As you can see, as you increase, so this is for a zero drain to drain voltage. So this is the drains extension region, suppose. As you can see, the gate voltage modulates the electron density in the drains extension region near the channel. So if the gate voltage modulates that greatly, then if you, for every value of drain voltage, for a certain value of gate voltage, there was a certain electron density here. Now you increase the drain voltage. When you have increased the drain voltage, the corresponding value of gate voltage would also increase. For carrier density to be this much. Suppose carrier density is now this much for 0.4 volts. Now you increase the drain voltage. Then this much carrier density in the extension region, this is the drain voltage is directly connected to this drain extension, isn't? So what happens is now you need to increase the gate voltage also correspondingly, so that the carrier density is again this much. Okay. So what now happens is, for a positive charge here, for a negative charge dipole, negative charge to be present in the fin, it depends on both the gate voltage and drain voltage. Okay. So for a positive charge in the gate, if negative charge, corresponding negative charge is not available in the drains extension region, you would find a small value of capacitance, gate to drain capacitance. If you find corresponding amount of if you find negative charges amply available in the drains extension region, you would find a large gate to drain coupling capacitance. Did you understand this point? So if you find a small value of if the electron density in the drains extension region is small, the corresponding capacitance between gate and drains extension region would be small. If the electron density in the drains extension region is large, then the capacitance between gate and drains extension region would be large. So that is the kind of, so what happens is, if you therefore if the electron density in the drains extension region is dependent on the value of gate potential and drain potential. It is dependent on VGD, gate to drain potential. So now gate to drain potential difference would define the electron density in the drains extension region, and thereby the value of fringing field capacitance between gate and drains extension. The value of fringing field capacitance between that is CGD is now determined by the electron density in the drains extension region, which is determined by value of gate voltage and drain voltage. So this is a P MOSFET. As you can see, you can think of it as several parasitic drain extension transistors are there. Okay, and as you increase the gate voltage, these are turned on or off. It's as if the electron density here is getting, so it's as if the source of, there is a parasitic transistor here with its source connected to the drain pad, drain connected to the channel, and gate connected to this gate through a fringing field. So there is it's as if a parasitic transistor is present here. So this gives rise to a strange issue that, I'll just finish it here. Right. When you, suppose this is input voltage increasing at this inverter's input. When you increase the input voltage, at a certain voltage, the drains extension parasitic transistor is on, and after that voltage, so when you increase this input voltage, the P MOSFET's drains extension parasitic transistor is off at a certain voltage, and beyond that input voltage, what happens is that the capacitance seen at the PMOS input is smaller. So if you increase the and this is the output, this is input corresponding output, this is increased input transition time corresponding output. Okay, so what happens is the overlap, when you increase the input transition time, you can see the overlap between this here to here, the input to, this is input to output overlap. So between this region, what was the input to output overlap? Input voltage changed from here till here, and the output voltage only changed till this point. Okay, it did not go down much. When you increase the input transition time, the output voltage changed a lot within, by the time the input voltage rose to this value, the output voltage reduced by a large value. So input to output coupling is now larger, for say till this point the capacitance is large. The P MOSFET's drain extension capacitance is large till this point. After that, the drain extension parasitic transistor is off, so the capacitance is small. So till this point, what is the overlap that between input and output? That is what is to be seen. So that defines the input capacitance. So if you keep on increasing the input transition time, you find that the input capacitance keeps on increasing. The effective input value of input capacitance keeps on increasing, and that is a very strange result, and that's what again happens for parasitic capacitance. So the capacitances are highly dependent on transition times if you have an underlap kind of FinFET device structure. So this is where I'll stop. So now we can have some discussion. So what I have done is I have given a general introduction to FinFETs, their operation, and width quantization effects, and parasitic effects, and one of the implications of parasitic effects. Yeah. Okay. Bottom of silicon film. It depends on whether it is. I'll come to that kind of a picture.
Actually, ask.
Yeah. Here. So what by bottom you mean this point? Huh? Yeah. It depends on whether it's an SOI FinFET or a bulk FinFET, isn't? So it would depend on whether it's an SOI FinFET or a bulk FinFET, and the potential and electric field. Suppose, see, in the middle regions, it is fairly the electric field is fairly straight from the interface to the midpoint of the fin, isn't? So if this is the interface and midpoint of the fin, it is fairly straight. But at the bottom, you would have the electric field lines fringing into the. Suppose it's an SOI FinFET, then you would have electric field lines fringing into the buried oxide also, isn't? So the electric field within the fin would not be like what it is in the middle of the fin. It would be smaller. The value would be smaller, and the electron density also, in my opinion, would be smaller at the bottom of the fin. Is that fine?
Good morning, sir. Myself, Nidhi Gupta from
Any other query?
ABS Engineering College. My question is, actually, I was wondering that when for
What biasing? Body biasing. Yeah. See, body biasing is possible in bulk FinFET, but its impact would not be so great as in planar technologies. Even in planar technologies at short channel lengths, you know that negative reverse body bias is not much effective, because the depletion region from the drain and source already occupy a large part of the channel, isn't? So it's forward body bias which has some effect, some influence on the planar technologies. In the FinFET technology, you know the fin is quite thin, so the gates control is large, and there is no depletion region as such. It's all bulk inversion, and depletion region kind of effects are very low in a FinFET. So body bias, in my opinion, would have an impact in bulk FinFET, but it would not be. It would be a minor impact. It would not be as great as in a planar technology. So, yeah. This that is a very difficult question, because it has answers according to the kind of device structure that people are proposing. Someone proposes an underlap device structure, others propose an overlap device structure. So, but yeah, UTB, you are trying to compare UTB SOI, ultra thin body SOI and FinFET, isn't? That's what you are trying to compare. So if you, yeah, so in that, at 22 nanometer node, see, any time FinFET would give a better gate control compared to ultra thin body device, isn't? It would give a better gate control and more bulk inversion also. See, because bulk inversion would, because of the two gates on both the sides, there would be bulk inversion in FinFET. In ultra thin body device, there would be bulk inversion, but the inversion with charges would mostly get crowded near the interface. So that way, always ultra thin body device would have a lower performance compared to FinFET. But the problem is that ultra thin body devices are, in my opinion, easier to manufacture compared to FinFET that way, because you have only one gate. It's more planar compatible. FinFET is also planar compatible, but I think UTB devices would be even more easier compared to FinFET. So that's the major attraction for UTB devices, FDSOI, isn't? So FDSOI would give a performance which is relatively good, may not be as good as FinFET, but the manufacturing process is much easier, isn't it? So, and these kind of issues like width quantization, etc., are not there in ultra thin body devices. Okay, so that way, I think it is better. But anyway, ultra thin body will not be supported as you go for the major. The basic idea these days that people have is that it would not be supported if you go for a smaller channel length, even smaller channel length, because then gate control has to increase.
One question from JCLC Union Jaipur. As we have just discussed, there are certain design issues associated with parasitic resistance and persistence.
Yeah.
Then in practical applications, how FinFET structure is advantageous?
Yeah. Say even without handling all those issues, even if you use a very straight planar like circuit design methodology, FinFET gives a better performance than planar devices, equivalent planar devices. Okay, that's because of better gate control, very small, very small parasitic. See, parasitic effect of extension regions are great, but the intrinsic parasitic, intrinsic capacitances themselves are quite small compared to planar technologies, and that is the, I mean, planar cannot be scaled beyond the point. So that's why the intrinsic, these do not have the capacitances associated with source drain junctions. There are several capacitance effects which are not there in FinFET at all, isn't? So therefore the circuit performance is better, even when you don't handle all the parasitic effects at a circuit design level in a systematic manner. The circuit performance is good. So if you handle all of them properly, it will be even better. That's what I was saying. So that's why it is working, in my opinion. That is my personal opinion.
Okay, next question please from any other center.
Good morning, sir. Myself,
Sir, my question is, what about quantum tunneling effects on the double gated effects?
Yeah, quantum tunneling effects. Yeah, it would be there if you have thin gate oxide. But nowadays the idea is to have a thicker oxide, thicker dielectric, high K dielectric and a metal gate. So thereby avoid the tunneling effects, gate tunneling effects. Isn't? And the other thing is, because the gate control is better, anyway have a thicker gate oxide. For example, in gate all around devices, I find that mostly the oxide thickness being used is relatively large, because anyway the gate control is good. Yeah.
So, if we apply more current to the both gate terminals, it doesn't, what is the pinch of both these effects on the channel?
If you apply gate and
If we apply
more current,
in transistors,
huh?
in the time, what about the channel?
What about?
Pinch of voltage?
See, in these devices, it's not pinch off related. You are talking about the saturation, isn't? Transistor saturation because of pinch off.
Yes, sir.
See, these devices are not pinch off related saturation devices. See, these devices are so small. The channel length is typically say 11 nanometer, 14 nanometer, or 11 nanometer or so. Even for very small drain voltage, you would find velocity saturation. So the saturation itself is not because of pinch off, but it's because of some other mechanism in these devices. So pinch off is a long channel related saturation mechanism. It is in these devices, it's not pinch off related saturation mechanism, it's some other mechanism. It is related to velocity saturation and the extension region carriers, how they are controlled by the gate voltage. It's a different saturation phenomenon, and in my opinion, even now people are working on these topics.
Next query please.
Okay, sir. So my question is, while doing analog layouts, I want to ask that is there any possibility of velocity input effect in
Yeah, velocity overshoots are there as you keep on reducing the channel lengths. Velocity overshoot and ballistic transport, these issues would anyway be there, and most of the transport theory now people are looking at is they're not trying to perhaps use uh, this Lundstrom's formalism, where you have a virtual source and ballistic effects are properly taken into account. The velocity overshoot effects would be there.
So one more question is that do you see the single electron transistor advantages over FinFET technology?
Okay. See, single electron transistor, uh, these are, see, then you have to find out what is an equivalent FinFET device for a single electron transistor. So one has to compare for equal value of I of for a certain value of I of, what is the ion for a SET device and what is the ion for an FinFET device. What are the capacitances of SCT devices? So if I realize an inverter using SCT device, what are the capacitances seen? What are the speeds seen? I mean, one has to compare even from the capacitance point of view, because circuit performance is highly dependent not only on the current drive but also on the capacitance. So I don't think such a thorough comparison has yet been done.
So any query from any other center?
Good morning, sir.
Good morning.
I am listening from RD project. So what is the body pattern?
What is the
Body pattern.
okay? So let us look at the planar device. Yeah. So here this is body. Okay, if you can see. So this is connected to, I mean, this is the source you can see, and drain, gate. So now source is suppose grounded, drain is connected to any voltage, high voltage, or maybe it's also grounded. The gate is now at a high voltage. Okay, body is suppose connected to ground. Okay, I'm trying to explain in a very basic layman kind of way. So there is a channel formed. Suppose the gate voltage is higher than threshold voltage, inversion channel is now formed. Now when you increase the body voltage, okay, suppose you tie the body voltage to a negative, reverse bias the body to source junction, that is you give a negative body bias here. Suppose you, yeah.
Body voltage means input voltage.
No, body is this body, this is body, isn't? Wherever I am pointing the cursor, I am pointing the cursor to the body. If you can see, this is the body. Okay, so if you ground the body and you have a certain gate voltage and inversion charges are formed here. Now instead of grounding the body, you connect it to a negative voltage, suppose. Okay, so when you connect it to a negative voltage, the source to body junction is now reverse biased, isn't? And there is a depletion region between the channel and the body. Okay, so there is a negative channel here, N channel formed, there is an electron channel formed here, and this is a p-type substrate. So it's as if there is a reverse, this p-type substrate, you have given it a negative potential. So it's as if there is an N channel here, N-type region here, and a p-type region here. The p-type region you have given it a negative bias. So the depletion region between this N-type and p-type substrate, N-type channel and p-type substrate, the depletion region thickness has to increase, isn't? So if that has to increase, the N-type, this N-type channel is highly, it's having a high electron density. The channel has very high electron density, and this p-type substrate has low substrate, the doping density. The doping density in p-type substrate is low relatively, isn't? So the depletion region extends more in the low carrier area, isn't? So it extends more in this p-type substrate, and that depletion region is negatively charged acceptor ions. Okay, So now the gates positive charges are supported by these electrons inversion charge here near the interface, as well as these new negative charges that which are now part of the depletion region, isn't? So the gate, same amount of gates positive charges are now supported by inversion charge as well as this newly added depletion charge. So the inversion charge has to reduce in some sense. So you think about it. So that's how, due to body effect, that is a negative body bias here, you reduce the inversion charge density.
So I think if there is no more query, then we can stop here, and then we can have a break of 20 minutes, and then we will be again back with our expert, Dr. Anand Bulushu, on our next session. We are really thankful to you, sir, for this nice session.
Thank
And
you for. I mean, I have also been able to interact with so many people.
yes.
So that's
So just we will have break for 20 minutes, and we will be right back at 11:30. Thanks a lot. एक मिनट presentation second one. Dear participants, welcome once again after this tea session. So, Dr. Anand Bulushu is again here with us for his next presentation on nanoscale VLSI circuit design. So, I request Dr. Anand Bulushu to kindly continue with his session. Dr. Bulushu, please.
So today, the mic is on. Today, in this session, I'll discuss regarding the circuit design methodology, mainly how circuit design methodology is done in a modern CMOS technology. So, and then some issues and how they are dealt with, issues related to modern CMOS planar technologies and how they are possibly dealt with. Okay, so first we'll build a framework of how circuit design is done. So what do we mean by circuit design? In circuit design, one of the major things is how do we size transistors, and then how do we lay them out. Okay, so this is back end circuit design. Okay, so first I will discuss what are the major timing issues in VLSI circuit design, and then I'll in some detail, in a good detail, I'll discuss the method of logical effort, because that is a framework on which the variability aware circuit design can be done, in my opinion. And variability and nanoscale circuit design has to deal with process variability. So as you can see, this is the modern microprocessors have so many transistors and gates that you cannot do without design automation. And and design automation is mostly standard cell based circuit design, and standard cells have to be carefully designed. So transistors in a standard cell need to be carefully sized, and there are not few standard cells, there are thousands of standard cells in a library, around 2000 standard cells in a library. So you cannot keep on designing, you cannot keep on laying out each standard cell and extracting, again redoing it. You need a methodology to do it. You need a methodology to size the transistors in a standard cell, and you need a and you need an EDA tool which properly places right size transistors, standard cells, cascading all of them. Okay, because standard cells need to be cascaded one after another. So how to choose the, for example, there would be inverters of around 40 sizes. There would, sizes mean transistor sizes. There would be NAND gates of about 20-30 sizes. Okay. So then how to cascade, which size to cascade after what. So there is a methodology to it. So that goes inside a CAD tool, but a designer should know what is going inside a CAD tool also. And while designing the standard cell, he should have a methodology to size the transistors in a standard cell. Likewise, the critical parts of the circuit, critical paths of the circuit are usually full custom designed. That is, you size all the transistors and lay them out carefully and almost manually. So for that also you need a methodology to do it. So that methodology we will discuss today. So that methodology is one of the methodologies for doing it, and I think the most popular one is the method of logical effort. So this is what I will discuss today first. Then I will discuss how using the method of logical effort we can handle the issues of process variability. So for the method of logical effort, first let us discuss the delay model. See, it's a method to optimize, minimize delays. It's a method to optimize transistor sizes or gate sizes so that the delays are minimized. So first thing is, let us assume that the gates are sized, inverters and other gates are sized such that the output transitions, rise and fall transitions are equated. Suppose they are sized in such a way. The WP, WN are chosen in such a way. Okay. So that is the first assumption. Let us take it. And now we want to derive a delay model for the inverter. So why do we want to derive a delay model? That is because we are trying to minimize delays for gate sizes. So for choosing, how do we choose in a cascade of gates? Suppose there are 10 logic gates cascading each other, implementing some logic function in a data path. We want to minimize the delay of that data path and size the logic gates in such a manner that the delays are minimized. So we want a delay model first of all. What should that delay model be based on? See, in a cascade of logic gates, the output capacitance of each logic gate would logic gate would be a capacitance, because it's a MOSFET logic gate. So MOSFET logic gate would have a capacitive input. It would not have a resistive input, isn't? And so one of the parameters should be what is the output capacitance for the delay model. The input parameter for the delay model should be output capacitance. The other one would be, I have a logic gate, what is its, for example this inverter, what is its input transition? So what is the output capacitance, what is the input transition? These two should be the parameters for the delay model, isn't? So but now we will first derive the delay model for a very restricted case. That is the case of where the input transition time is somehow proportional to the total output capacitance. And this case is not a bad case, it's a very good case for critical paths, optimized critical paths, as we will see later. So it looks like a very hard restriction, that why are we trying to derive a delay model for this input transition time being proportional to total output capacitance, but that is what we will do now, and we will see that it leads to a delay model for only this condition, while this condition is being fulfilled, is not a bad delay model. It's it's applicable in the most important cases, most significant cases. So what we find here is so what is this CP? Let me define it first. So that is the capacitance, parasitic capacitance looking into the output node of the device. So total output capacitance would be C out plus CP, isn't? Right. So what we are saying is, if I increase the input transition time by alpha times, I would also increase the total output capacitance by alpha times. Now for this inverter, I cannot increase CP. So I would increase C out by a larger value than alpha. Then the total value C out plus CP would increase by alpha. Is that fine? So this is what I am doing. So in this condition, I would like to look at delays. So in this condition, what would I find? So I will very briefly go over this. So when I increase this by alpha, so while this is um, increasing, you can see that for every small section, so take a very small section initially. So in this small section, there is an average current which is flowing. That average current, that so initially at this point, where was it? There is, this cursor is creating an issue. So suppose you are dealing with this 0 value of input to this value of input. So at this point the output voltage value was VDD, and here it is as when you come here it is a certain value, this value suppose. Okay, so only the output voltage has fallen by only this value. So now there is an average current between this, and what is that average current determined by? It is determined by how much is the, for a certain input increase in input voltage, the average current would depend on what is the input voltage range, change in input voltage, and what is the change in output voltage, corresponding change in output voltage. So output voltage, so if this is a small change in input voltage, then the input had started from 0 and output had started from VDD, isn't? So the current, if it is a small, if you take a very small incremental increase in input voltage, the average current would depend just on the output voltage value, which is VDD, and the change in input voltage, isn't? Delta V in. Okay, delta V in VDD, the average current is determined. Okay, so within that small change in input voltage, the average current is the same. So average current into that time would determine the drop in output voltage, isn't? Average current into time would determine the output discharge, isn't? Okay, so shall I use a board or something, or that would make it easier to understand, I think. So this slide as well as the board, both would be visible on the screen. Is that possible? That slide and the board both would be visible on the screen?
Both not visible at a time.
Achha.
They can be visible after 1 hour.
I'll try to do it that way. Suppose this is the input and this is output. Okay, so here between, take an incremental delta V. So in that small delta V, suppose average current is I. Okay, so corresponding discharge, output discharge is delta Q, okay, because this delta V into delta T. Okay, so whatever is the average current into delta T is the, this is equal to the average current into delta T. So now what you have done, you have increased the, suppose you have increased the output, total output capacitance by alpha times, and input transition time also by alpha times. So this delta T would increase by alpha, isn't? So delta Q would also increase by alpha. What is the change in output charge, output voltage? The change in output voltage initially was delta Q by C out plus Cp, isn't? You are saying that when you increase input transition time by alpha times, that is delta T by alpha times, this you are increasing by alpha times, and current also, the average time is also increasing by delta times, so therefore charge is also increasing by delta times. So the change in output voltage is again the same. Am I making sense? So the change in output voltage is again the same. So what is happening here is, when you increase the input transition time by alpha times and you keep the total output capacitance also, it also increases by alpha times, then for a given change in input voltage, the change in output voltage is the same, isn't? So likewise, if you keep on going ahead along this transition, the change in output voltage for the full change in input voltage, this VDD minus V out of TRN would come out to be the same. For this, if this condition is followed, that's one thing. What after the input transition time, input transition is over and input transition value, input voltage value is VDD. What happens after that? Let's now discuss that. Now take a small incremental decrease in output voltage. Okay. So if you take it, now input voltage is fixed at VDD, an incremental decrease in output, what we are saying is, so whatever be the increase in input transition time, if you follow this condition, then V out of TRN remains the same. That is, when the input transition is over, what is the reduction in V out? That remains the same. So V out of TRN is the same for all values of TRN, while this condition is followed. For all values of TRN, it's the same. So now, an incremental decrease in output voltage is from this V out of TRN for any value of TRN, isn't? So for and input voltage is fixed at VDD. Now it has reached VDD and it's fixed at VDD. So input voltage of the inverter is fixed at VDD. Output voltage is fixed at V out of TRN. A small incremental decrease in the output voltage would lead to an average current. Within that incremental reduction in output voltage, the average current would be the same for all values of TRN, isn't? So what does that mean? So for an if you increase the value of TRN and Cout plus Cp by alpha times, then for a small for an incremental reduction from V out of TRN, the output current is again the same, and therefore it would take alpha times more time. That delta V out into Cout plus Cp is now alpha times, and output current is the same, isn't? So it would again take alpha times more time. Is that fine? So now what if this is the 50% input point, 50% output point, the time gap between them would increase by alpha. If you increase input transition time by alpha times, the delay, 50% delay would increase by alpha. Does it make sense? It's a very generic statement. I am not going into current equation or anything. For any current equation, if the current is a function of VG, input voltage and output voltage, this whole thing is followed. It's a very generic kind of dealing with the problem, isn't it? So what we are saying is, if this condition is followed, then delay would also increase by alpha times. It's a very common sense kind of argument that we have put forth. So delay, so if I plot delay versus Cout by Cout plus Cp, total output capacitance, or delay versus TRN, it's one and the same, because Cout by plus Cp and TRN are proportional. I should get a line, straight line, going through origin, because it's all proportionality relationship. Delay versus Cout plus Cp is proportional now, isn't? And delay versus TRN is also proportional. So I should get a line going through the origin. If I plot delay versus TRN, it should go through origin. Delay versus Cout plus Cp, it should also go through origin. Isn't? And a straight line. Okay. So now if I increase this, in this inverter, I had initially said that Wp by Wn is fixed, and that has been fixed to equate the output transition time. Suppose it need not be, but in this case, suppose it has been done, but it is fixed to equate the output transition times. Suppose. So now Wn therefore defines the size of inverter. Okay. So now suppose Wn has increased. Suppose you increase the size of inverter. That is, you increase Wn. Proportionally, you increase Wp also. So what have you done? In other words, you have increased that current. You have increased current drive. Okay. So what would happen? So for whatever value of whatever was the earlier value of delay, you have increased current drive everywhere. So to obtain the same value of delay, you would you would have to increase the value of C out by Cp by the same amount. So suppose you have increased Wn by 2 times, then you need to increase the total value of C out plus Cp by 2 times to keep the same delay. Okay, so if I increase C out by Cp by 1 value here, from here till here, for smaller Wn, suppose the delay increases by this much, for the same increase in C out plus Cp, for a larger Wn, the delay would increase by half the time. I mean, if the Wn is twice, isn't that right? So therefore, the slope for larger Wn would be smaller. For a larger Wn, the slope would be smaller. Isn't that right? Okay. So now we do another thing. We divide this C out by Cp by Wn. And then we plot this again from this point. Okay, delay versus C out plus Cp divided by Wn. Now all the lines would fall on each other. Slopes would all equate. Isn't that right? So see here, I have said that the slope is now proportional to 1 by current. Isn't? So current is proportional to Wn. So if I increase the value of Wn, slope reduces proportionally. Okay. So now if I divide this by Wn, the denominator you have current Wn, isn't? So if I divide this x-axis by Wn, what would happen to the slope? It's in denominator, isn't? X-axis is in denominator, and so that goes to the numerator again, and all of them fall on the same line. Is that fine? So now delay versus C out by Cp by Wn is the same line, isn't? For all the inverters, whatever be the size of inverter. Is that fine? But one condition is followed, that input transition time and total output capacitance are kept in proportion. Their proportion is not changed. Isn't? So that is one condition which is followed. Or in other words, input transition time and output transition time are kept equal. So if you keep the input transition time and output total output capacitance in proportion, what do you mean? You mean to say that you are keeping if you keep input transition time and output transition time equal, then input transition time and total output capacitance would come in proportion. Okay. Okay. So now let us do another thing to make it. What is the value of parasitic capacitance by Wn? So what is this parasitic capacitance due to? Let us think. So parasitic capacitance is because of gate to drain capacitance. Okay. It is because of drain to body capacitance. You know some basics of MOSFETs, isn't? So what is drain to body capacitance due to? It is because of junction. Okay. What is gate to? So let us again come to the board. Let us look at the. Let us look at the top view layout. So suppose this is a transistor. This is gate. This is channel length. So in digital circuits, you don't touch channel length, you don't reduce, you don't increase it, keep it at the minimum value. So there is this gate to drain capacitance. Suppose this is drain, this is source. Gate to drain capacitance, gate to source capacitance. Okay. So when you increase the bit, what would happen to these capacitances? They would increase proportionally. Isn't? And what about that body, drain to body capacitance? So let us draw a straight line here. Across it, let us draw the cross section. So this is the gate. So this is the junction capacitance. So this is body is P type in an N channel device. This is N plus type. So this is the junction capacitance, isn't this junction capacitance? So it is there all at all the places below this. Okay, so when you increase the width of this, this also increases proportionally. So parasitic capacitance is all because of these capacitances. Okay, so parasitic capacitance increases, you can think of it as increasing proportionally with width of the device. Is that fine? Shall I rub this off? So you can think of the parasitic capacitance as being proportional to width. So here, so Cp divided by Wn. Now you can come back to the slide. Yeah, is that fine? Right. So Cp divided by Wn in this should be a constant then. Technology dependent constant. It would be different in SCL's PDK, it would be different in TSMC's PDK, isn't it? It would be different for different foundries, but it would be a technology dependent constant, isn't? So if you take that, so now you have the C out plus Cp divided by Wn versus delay. It's a straight line for all the inverters. That's what we have discussed, whatever be their size. Now, if you want to draw only on the x-axis only C out by Wn, where would the origin shift? Origin would shift here to Cp plus Cp by Wn point. I mean, from this you would subtract Cp by Wn, which is a technology dependent constant, isn't? Then you get this new origin. Isn't that fine? So you draw the y-axis here, which is delay axis. Y-axis is delay axis. So wherever it cuts the earlier line, that we call parasitic delay. That we would call parasitic delay. See, since this line is unique to all the inverters in the technology, and this distance, that is Cp by Wn, is unique to all the unique to the technology. So this parasitic delay for all the inverters should be unique to the technology. Is that fine? So all these statements are valid for a certain layout style, because layout style would also determine capacitance, but let's not go into that. Okay. So a layout style is also followed. Keep that in mind for all this. So now this parasitic delay is unique to this given CMOS technology. Okay. And you have delay versus C out by Wn now, because now this straight line from here is C out plus Cp by Wn minus Cp by Wn, which is C out by Wn. So we have delay versus C out by Wn is a straight line cutting the y-axis at this point, which we call parasitic delay, which is unique for an inverter in a given technology. Okay, whatever be the size of inverter. Okay, so and what is Wn dependent on? Wn is proportional also to the input capacitance of an inverter. See, the input capacitance of an inverter, what would it be? If you increase the W, Cox into W into L. L you are not changing, it's minimum sized, it's at the minimum size possible. So Cox into W into L. So if you increase W, Cg increases by proportionally. Likewise, input capacitance has contributions due to gate to drain capacitance. That is also proportional to W, as we had just seen. So all the input capacitance is almost proportional to W, isn't? So C out by Wn here can be expressed as C out by C in of the inverter. The C in is the input capacitance of the inverter. So delay versus C out by C in should be a straight line, and that straight line is uniquely determined for any CMOS technology. Slope of that straight line. Okay, that slope. So we write it this way now. That's G delay is G into delta into C out by C in plus P into delta. I'll talk about all this now. Let us, for inverter, let us say that G is equal to 1. then it is delta into C out by C in plus P into delta. So what is this delta then? Delta is then the slope of this line. Slope of this line. If G is 1, slope of the line is delta. Isn't? So, and that is characteristic of a CMOS technology for an inverter. Okay, where WP by WN are kept constant. Okay, that ratio WP by WN is maintained. So, G is equal to 1 for an inverter, arbitrarily defined. Then delta becomes the slope for an inverter. When you draw this slope, delta becomes the slope, isn't? And express P also in terms of delta. So delta becomes a time unit for us. Is that fine? So for circuit design activity, delta becomes the time unit, and we call this delta as intrinsic delay of an inverter, intrinsic delay of technology. You can call it anyway. Okay, it's a very fundamental thing for circuit sizing, layout, etc. So this is the inverter's delay model which is used in logical effort. And what are the things that we have for what is the major assumption that we have made? Input transition time is equal to output transition time, or in other words, input transition time and total output capacitance are kept in proportion. WP by WN is maintained ratio, it's not changed. That's another thing. Okay, so then this fundamental thing is followed, that delay versus C out by C in would come out to be a straight line, and this parasitic delay would be characteristic of the technology for an inverter, and this thing is followed. For an inverter, J is kept arbitrarily at equal to 1, so delta is the slope of this straight line, and that is our time unit now, and we call it intrinsic delay of the technology. Okay. So now let us see how we would do buffer design using this method. Using this delay model. Okay. Now this is buffer is inverter chain, and it is a very common, fairly common circuit, because suppose you want to drive the, see, for example, you have a large microprocessor chip or any chip, and there is clock going everywhere. Clock, in fact, clock network, if you put all the clock wire in a straight line, it would come in centimeters. Itna so long. Okay, so clock loads, the clock load is a major load on the chip. Okay, and it is most frequently switched wire also in the chip, isn't it? So you need to drive it through using buffers everywhere. Okay, because it's such a huge load. If you drive it using a single inverter, that inverter's output load would be so large that the clock would never work. You need to keep on driving it at different places using buffers. So clock buffers, people say, consume about 40% of the total power. Okay, they are so important. Okay, likewise, in several other places, address buses, you need output buffers. You need buffers everywhere. And that's why you find that inverters are the most used logic gates. About 40% of logic gates used in a chip is inverter. Okay, inverters of different sizes. So let us first work out this buffer design example. How do we design a buffer? So what do we want to do in this design? We want to minimize the total delay of the buffer. And what do we have? We have the output capacitance, and we have maximum allowed input capacitance. We have the value of output capacitance. We have the maximum allowed input capacitance of the buffer. We don't have anything else. Number of stages n has not been fixed. It is to be optimized by us. Size of each of these buffers has not been given. It is to be optimized by us. So number of stages n and size of each of these inverters has to be optimized by us in such a manner that the total delay of the buffer is minimized. Total delay of the buffer is minimized. Output capacitance is already given, and the maximum value of input capacitance is given. Why maximum value of input capacitance is given? Because this input capacitance is driven by some other circuit. So its maximum, that circuit's maximum output capacitance is fixed. So that becomes the maximum value of input capacitance of our buffer. Okay. So we will work with this maximum value of input capacitance. We will say that I'll design buffer for this input capacitance itself. So C out is given, C in is given. What is the delay of the buffer? Delay of first stage, second stage, nth stage. I don't know what is the n. Okay. So now first let me do for a given n. Then I'll try to optimize n also. First I'll not optimize n. I'll say that I'll use for a given n. Then I'll go for optimized n. Okay. So now what is the delay? Now I'll write it. I'll somehow imagine that input output transition times of each of these stage are made equal. I'll later see that they actually become equal if I do something, and that is a good case actually. That also reduces short circuit power if you equate input output transition times. But okay, so let us assume that input output transition times are all equal. So then our delay logical efforts delay model is valid. So what is it? G1 into C out 1 by C out 2. C out 1 is, by the way, C in 1, C in 2. C out 2 is C in 3, isn't? C out K plus C out K is C in K plus 1. Isn't that right? Here. So I'll write G1 into C out 1 by C in 1 plus P plus G2 into C out 2 by C in 2 plus P. So all those P's can be added here, and all the G C out by C in terms are added here. This P is a fixed value, technology dependent. That cannot change for a given n. I'm not first I'm talking about a given n. At a given n, how do I size all the transistors, all the inverters? And within the inverter, W pi by Wn is fixed. So if I size the inverters, I size the transistors also. Is that fine? So for a given n, how I size the inverters in this buffer so that delay is minimized. Later I will optimize n also. Okay. So what is this now? So I have sum of all these terms to be minimized. This is already a fixed value. This cannot be changed. P, sigma P cannot be changed. So this I want to minimize. What is the product of all these terms? It is pi of all these G's. In inverter's case, G is all 1. So it is 1 into C out by C in 1. See, C out by C in n into C in n by C in n minus 1 into C in n minus 1 by C in n minus 2. Likewise, C in 2 by C in n. C in 1. Isn't? So that becomes C out by C in 1. Now it is a fixed value. This pi G is 1. C out by C in 1 is fixed. C in 1 is the maximum value allowed that we are going to use, and C out is fixed, isn't? So now C out by C in 1 is fixed, isn't? So the product is constant. Product of all these terms is constant, and sum of all these terms is to be minimized. So there is a theorem in maths which says that if the product of terms is fixed, constant, and sum of terms is to be minimized, all the terms must be equal in value. Okay, so we can derive that theorem. Will not do it here, but that can be done separately. But that is so now we get a hint of what to do. So what is the hint? Hint is that are you able to see? नीचे दिख रहा है या? हाँ, you are able to see this point? है ना? D1 equal to Dn. So you need to make all these D1, D2, Dn equal for a given n, isn't? What does that mean? Then the delay is minimized. Delay of the buffer is minimized. Okay. What does that mean? It means that see this all G's are equal, isn't? They are all equal to 1. So it means that C out by C in of each stage must be made equal. Okay. Or in other words, C out by W of each stage must be made equal. Okay. So if C out by W of each stage is equal, doesn't the transition times everywhere become equal? This again confirms our first assumption that transition times are equal. See, transition time is just dependent on C out by W. It is dependent on C out by I. I is proportional to W, current drive, isn't? So C out into delta V, C out into VDD by I, roughly the transition time. So transition time, how much is the charge to be discharged divided by drive current. So C out by C in is, if it is equal for each stage, transition times everywhere would be equal, isn't? So our assumption that transition times is equal falls properly. So if that is followed, then all these terms must be equal because of this condition that product of all these terms is a constant. Then all the terms must be made equal. All the terms must be made equal means C out by C in of each of these terms must be made equal. So how to find that out? That is C out by C in to the power 1 by n, isn't? So if I just do a product of all these, there is the cursor. If I take C out by C in, this capital G is product of all G's, which is 1. Capital H is product of all C out by C in. Small h is C out by C in of individual stage. Okay. So capital H is product of all the small h. Okay. So which is C out by C in 1 in this case. In this case, this capital H is going to be C out by C in 1. That is fixed, isn't? So take C out by C in 1, do and take its 1 by nth exponent. Okay, C out by C in 1 to the power 1 by n. That is the value of small h. Okay, that is the value of individual C out by C in 1, isn't? So take the value of C out, find out total C out by C in 1 to the power 1 by n, isn't? So C out by C in 1 or C in of the nth stage would be equal to that. Each stage is equal to that. So nth stage is also equal to that. So C out by this value, whatever h you get, is C in n. C in n minus 1 in C in n divided by again h. Likewise, you come to the first inverter. Okay, that is how you. So you have fixed the C in of each of the inverters. C in and W are proportional, Wn are proportionals. Find out Wn. Wp by Wn is again constant. Find out Wp. So you have sized all the transistors. Okay, this is the sizing methodology based on method of logical effort for a buffer. But now we have not completed the story because we have not found the optimum value of n yet. We have done it for a given n. So how much time is left? Was 11:30 to 1. 11:30 to 1. So about half an hour more is left, isn't? Right. So I will try to finish off at least this, if not the how to handle variability part. So now what do I want? I want to find out optimum value of n. So what is that? So what is the total delay now? Delay can be written as, let me write it down here. So or else I think it's not required. Or let me write it down here. So can you show the board again? Total delay is now. So all the terms are equal, isn't all the total delay is C out by C in 1 to the power 1 by n. That is this small h. Okay. So total delay is d1 plus d2 plus dn. Okay. And d1 is what? d1 is g into C out by C in. C out 1 by C in 1. Okay. So this is C out K by C in K minus 1. So this must be made equal for all the C out K by C out K minus 1. This we are calling H, and H must be made equal for all the stages. That was our conclusion, isn't it? And delay of each stage is now like this. where G is equal to 1 because it is inverter. Because it is inverter. So total delay is all this. So added. So what is that? That is H into G. H is given by this. Is it? H into G plus H plus sigma P. So parasitic delay, and this is n times. This is also n times. Isn't? So what is that? N into H plus sigma P. Or sigma P is also n into P. N into H plus n into P. Isn't? Fine. So what is H? H is n into C out by C in 1 to the power 1 by n. 1 by n. Okay. Then, so this let us call capital H. So it is n into capital H to the power 1 by n plus n into P. That is the total delay. Isn't? Let's come back to this one. Come back to the computer. Right. So here what we had said was the delay is what? N into H to the power 1 by n plus n into P. This is the delay, isn't? And we want to optimize n. So this derivative should be equal to 0. That is the optimum value of n. So it is, and what is this capital T? Total delay n into H to the power 1 by n plus n into P, where capital H is C out by C in 1. Okay. So now isko derivative. So we need to find the derivative of this. So what is this f? F I have called this G into capital H to the power 1 by n, where G is 1 in inverter's case. It's an inverter chain. So capital G is product of all G's, and each G is 1. So it is actually H to the power 1 by n. F is H to the power 1 by n. So let us find out this derivative. So what is it? It is f minus n times f into natural logarithm of h into 1 by n square. Shall I derive this, or can you derive it? You try to derive it, we can do it offline, or otherwise I can do it on board now. So this, what is the kind of expression that has come out? This n and this n square, they cancel each other. So it is 1 by n only which is remaining here. Okay. So 1 by n natural logarithm of h. What is that? Natural logarithm of h to the power 1 by n. Hai. So it is f minus f into natural logarithm of f plus p. Okay. So the equation is coming in this form: rho into 1 minus natural logarithm of rho plus p. ऐसा एक equation आ गया. So this is the equation which needs to be equated to, I mean this is equated to 0 now. So this equation is a fairly general kind of equation. So it is not dependent, this p is a technology dependent constant. Rho is now, we need to optimize this rho. Rho is what? Natural logarithm, rho is h to the power 1 by n. I have again, why I have changed it from f to rho, I will tell you. F could be a non-optimized thing. Rho is the optimized value. I mean, rho is the value at which this equation is followed. You just take this f to be equal to rho. That's all. So I am just f minus f into natural logarithm of f plus p. So it is rho minus rho into natural logarithm of rho plus p, isn't? So just take that rho out. Rho into 1 minus natural logarithm of rho plus p is equal to 0. This is the equation which, if followed, gives me ideal value of rho. And what is rho? Rho is h to the power 1 by n. So that gives me also the ideal value of n. Is that fine? So if this equation is followed, I get the ideal value. This equal to 0 is followed. I get the ideal value of rho. Once, and what is that rho? Rho is h, capital H to the power 1 by n. So for a given, so I also get the ideal value of n through rho, isn't? So what is that? So once we plot this, this is equal to 0 on a using MATLAB or whatever simple software, software, you get that this rho almost follows a straight line given by this. Rho is ideal value of f, as I have written, and that is equal to 2.81 plus 0.71 p. You get rho is equal to 2.81 plus 0.71 p. It's just a function of p. As you can see, this is equal to 0. Rho into 1 minus natural logarithm of rho plus p is equal to 0. It's just a function of p. और किसी का function होना नहीं चाहिए, isn't? So it comes out to be a straight line like this. Rho is equal to 2.81 plus 0.71 p. Okay. So for a given p, rho is now uniquely defined. So what is that rho? Rho is ideal value of h to the power 1 by n. So what is n? N, वो कितना होगा then? So rho to the power n is equal to capital H, or in this case GH. I have written it in a generic way, that's why I am writing it as GH, and that has advantage later on when we introduce other logic gates. That's why. So rho to the power n is equal to GH. So what is n? N is log GH divided by log rho. Is that fine? So now I find n. N should be an integer, I know. N should be an integer. Number of stages cannot be non-integer. N is ideal number of stages. So ideal number of stages has to be an integer, and therefore, and this could be a non-integer which you get. You just go to the higher value, which is higher integer value. Suppose it comes out to be 3.4. Then take 4. By 4, we'll discuss that later. Okay. Yeah. Here we discuss that. So if you plot non-ideal value of n, number of stages is n. Non-ideal, if you plot, this is n cap is the ideal value of n, which is got in this manner. Okay, in this manner you get the ideal value of n, which is n cap in this plot, isn't? N is non-ideal value of n. Delay with non-ideal value of n you can get how? Just h to the power that non-ideal value of n, that is f, n into f plus n into p. Okay, so non-ideal delay divided by ideal value of delay. Okay, delay with non-ideal value of n, delay with total delay with ideal value of n, you can compute. So if you plot this, you find that minimum obviously exists at n is equal to n cap. It should be the minimum delay comes out at n is equal to n cap, as it should be. And when you reduce value of n, the increase in delay is faster, and when you increase value of n, the increase in delay is slower. That is, if you increase the number of stages by a small amount, the delay would increase from the ideal value of number of stages. The delay would increase, but it would increase by a small amount. If you reduce the number of stages from the ideal value by the same amount, the increase in delay would be larger. So if you, that's why I was saying if you get 3.4, take 4, not 3, as the ideal value of number of stages in that buffer. Is that fine? So I will not go into this. This will be quite confusing, or shall I? Because there is time left, so shall I go into this or shall I go into this? This would be more interesting for everyone. I'll go into this. I'll not go into branching effort and all that. That branching effort deals with this problem, that suppose there is branching of the path, then how do we size? We have till now discussed only a single path, isn't it? So I'll not go into that. Then there is this fork. Suppose there is clock, and the clock and clock bar are to be generated, and they must be synchronized. In the sense, clock and there should be no skew between them. So how to do that using the same method, that is fork design. I will not go into that right now. I will directly jump to other complementary gates. Otherwise the story doesn't seem to be somewhat complete. So I will try to do it this way. So for other complementary gates, how do we handle? So what was our delay model derivation based on? Our delay model derivation was based on just this, that current is a function of input and output voltages. Current is proportional to W, and the ratio of transistor widths in the inverter WP by WN is maintained. If these three conditions are valid, then input transition time and output transition time are kept equal. That delay model is valid. Okay. So now suppose now we do it. Now we find out equivalent sizes of other gates compared to a NAND gate. Okay, with NAND gate as a reference. Now let us find that out and see whether we can apply the same delay model for other logic gates. So we will take simple examples, because simple examples give a better idea. Complicated things we can do later. So we will take simple example of 2 input NAND gate and 2 input NOR gate. We would say that both the inputs would switch simultaneously very rarely in a circuit. One of the inputs would switch, isn't? Suppose B is held at VDD, A would switch from 0 to VDD and output would go from VDD to 0, isn't? Both switching simultaneously is a rare case, because both the signals would come from some different sources, and both of them therefore switching simultaneously would be a rare case. So that rare case let us not handle now, and let us design the circuit for more generic cases. Okay, so the generic cases is both of them would switch not simultaneously. So one of them is at, suppose one of them is at VDD, A is at VDD, B is switching. Then for a given output load, I want to get equal value of fall delay. So roughly what would I do? If the size of WN here was 2, I'll keep the size of these two transistors double sized compared to the inverter, because it's as if the current is halved because of the series transistors. Because of series transistors, it's as if resistance is doubled. Okay, the path resistance is as if doubled. It's a very rough statement. So the width is doubled. So now if width is doubled, you get an almost equal resistance as the NMOS here. Is that fine? So the delay is, so for a given load capacitance, if the load capacitance of both is equal, then the output fall delay would be equal, roughly. It's a very rough statement. Okay, so I will make equivalent N tree, and pull down network is now equal. Let us talk about pull up network. So in that pull up network also, I would say that both the transistor switching is a rare case. So and if the output is to charge high, both of them must be at VDD initially, and A, suppose both of them are VDD initially, A turns from VDD to 0. So now this is charging high. So this was twice the size. At this the transitions were equal, WP by WN being 2. So it is charging through a single transistor again. Load capacitance is the same. If I want to equate delays, I should keep the same size of the P MOSFET. So it is again 2. So pull up network 2 2, pull down network 2 2. If we do that, it's equivalent to this inverter. Likewise for NOR gate. For NOR gate, this is parallel. Pull down network has parallel transistors, so it has the same size as this. Pull up network has series transistors, so there the size is doubled. Is that fine? So now we have made, so but what we observe here, again the relative ratios of all the transistors is maintained. Is again maintained. Then WP2 divided by WN1 is constant. Likewise everywhere, the relative ratios are all now maintained, isn't? So So what were our conditions for assumptions behind the derivation of method of logical efforts thing? Input and output transition times should be equal. Current is proportional to input voltage and output voltage. Suppose this transistor is switching. Now what is the variable thing? This is at VDD. This is changing. This is changing. The current through this stack of transistors, what would it depend on? The only changing variables are input voltage here and output voltage here. So it should be again the current through the stack is a function of these two only. There is nothing else which is changing. So current is proportional to V in and V out. Current is proportional to W. If I increase W of this, I will also increase W of this. So the ratio will be maintained, isn't it? So current now W of both the transistors in stack is simultaneously increased if one is increased, isn't it? So any transistor you take is the correct. It would characterize the size of the entire gate, isn't it? So if the gate size is increased, the current drive is also increased by the same proportion again, isn't? So this value, this point is also valid. The third point is ratio of transistor widths in a logic gate is maintained. That we have first handled. So all the assumptions are valid. So this plot is again valid, and the delay model is again valid. Only thing is the slope would be different because the drive current is different. Drive current is stack's drive current. It's not the inverter's drive current. Slope would be different. Isn't that right? So now, but I want to use the same delta time unit that I had got for inverter. Inverter slope I had called delta. That was my characterizing time unit for the technology. I want to use the same thing. So now what I will say, G is different. And P is also different for different gates. Okay. So P and G are different for different gates. For NAND gate, G would not be 1. For inverter, G is 1. Arbitrarily, it was defined 1. That's why delta became time unit, isn't it? So I'll use that same delta as which I had got from inverter. I'll say that the slope is now G into delta. Whatever new slope comes for NAND gate, I'll divide this slope with inverter slope. That will become G for NAND gate. Okay. Likewise for all the gates, G would be different. Let me try to roughly estimate G. Have I done it later? No, I should do it here. Let me try to roughly estimate G of an AND gate. How much would it be? Now, this is the delay equation. Now, I would say that the delay of inverter, equivalent inverter and NAND gate must be equal. I will, for that, if the delays are equal, then I will, or change in delay is equal, then I will find out the value of G of NAND gate. Okay. So again, I'll have to resort to the board. So delay of inverter, what was what? It was C out by C in plus P, isn't it? P of inverter. Okay. G is 1 and time unit is delta. So I am not writing delta and delta anywhere. My time unit now is delta. G into delta वो सब नहीं लिखूंगा. I'll just drop delta. And delay of 2 input NAND gate is G into C out by C in of NAND gate plus P of NAND gate. I want to change C out by C in by the same factor. Suppose I want to change C out by C in by factor 1 in both the cases, and I want to see what is the increase in delay. Delta delay of inverter is equal to delta of C out by C in, whatever is the change in this. That's all. And delta delay of NAND gate is equal to G of NAND gate into change in C out by C in. It's all very common sense, isn't it? Nothing very complicated. So if the change in the delays must be made equal, then what must be followed? Let us see. This is Cin of the inverter, is it? And this is Cin of the NAND gate. I am saying that. Okay, so now. Okay, let me do it for a given change in CO. So I have changed the Cout by delta Cout value. I changed the Cout by the same delta Cout value for NAND gate. Okay, so here it would be Cout in C in inverter, here it would be Cout C in NAND. Isn't it right? And I want to equate the delays, change in delays. I want to equate the change in delays. Then what would I do? I should the C in inverter should be equal to G divided by C in NAND. Isn't? So let me estimate what is the C in ratio of C in NAND and C in inverter. So let us see. So here, okay, I'll draw it here, otherwise that becomes an issue. So what is the ratio of C in inverter and C in NAND? C in NAND is, look at one of the inputs, B or A, it is 4 times, and here we have 3 times. Suppose for a given width, for equal width PMOS and NMOS, suppose they give equal input capacitance, which is roughly true in general. Okay, so then the input capacitance here would be 3 units for the some 3 units, some unit which corresponds to 1, 3 units for the inverter. For NAND gate, for each of the inputs, it would be 4 units. Okay, so C in NAND would be 4 by 3 C in inverter. C in NAND, instead of C in NAND, I can write 4 by 3 times C in inverter. Okay. So if the delta delays must be equal, what would be the value of G? If, see, I am saying in these two cases, for a given increase in Cout, delta Cout, I had first said that I have sized these in such a manner, for a given delta Cout, the increase in delay would be equal for both the cases. See, this was one size, this was two sized, 2 times size. That was done to achieve this condition, that for a given delta Cout, the increase in delay for inverter and NAND gate is equal. So that I am following initially. The increase in delay, these two are equal for a given delta Cout. That I know. And in this, in denominator I have C in inverter, in this I have C in NAND. I am seeing from here that C in NAND is 4 by 3 times C in inverter. So I can just replace it here. I know that these two are equal. Then what must be G? G must be 4 by 3. So that is a rough way of calculating G. The correct way of getting G is plotting this here. Rough way of calculating G is comparing the input capacitances, okay, and getting the value. And the correct way of calculating G is plotting this for NAND gate, plotting this for inverter, taking the ratio of slopes. That gives more accurate value of G of NAND gate. But a rough way, back of the envelope method, which works fine in general, is this. So here you find the input make the NAND gate equivalent to input inverter, take the input capacitance of each node, divide it by the input capacitance of this thing, get the value of logical effort of NAND gate. Likewise for NOR gate, then it should be 5 by 3. Roughly. Accurate value will not be 5 by 3, but roughly it is 5 by 3. Is that fine? So what we are saying is this normalized delay versus C out by C in is, by the way, fan out. C out by C in, delay versus C out by C in. C out by C in is, by the way, fan out, isn't? So it should be a straight line like this for any gate and all that. Okay? Fine. So now let us see how do we optimize the number of stages in a logic path, data path. Suppose in a data path, so right now, so I'll just finish in 5 minutes then. Yeah, I have not gone into the topic of handling variability anyway, but I think this, I have tried to complete one part of it, okay, one sizing part of it, okay. Just to give a flavor of this. So now this is a generalized logic path, suppose a data path, and there you want to use the same method to size the data path. How would you do it? So now, as we had seen, the relative ratio of widths of transistors within a gate is maintained. Gate size is increased, then all the sizes of all the transistors are increased simultaneously. That's what we had seen, isn't? So in an AND gate, NOR gate, kuch bhi le lo, isn't it? Inverter. So that is the first thing that we are doing. Now again, let us put this whole thing here. So what are we saying? We want to increase the, minimize the delay by sizing the logic gates in this. It might so happen that, see, when you add inverters into this, would you increase delay or reduce delay? It seems it would increase because number of stages is increasing. But when you add inverters into this, and suppose you, okay, let us go into that later. Sometimes it may actually happen that when you add inverters, you may reduce delay. We'll come to that later, but let's not get into that. Let us do it for a fixed value of n. So in this data path, this is the number of logic gates which were there, which is in this case 4. Suppose it is n, and I want to minimize the delay for that given n. So what would I do? Again, I would do a similar thing as I had done earlier. So I would again write this equation d1 plus d, and now I will keep all these g's also there intact. That's why I had kept it, written it that way earlier, because it's double use then. So now I will keep all the g's, and now it is sigma of p. It's not n into p now, because it's not all inverters. It's a data path. All this here I have drawn inverters, but it's actually this kind of a circuit. Yeah, it's actually this kind of a circuit. Here, any arbitrary gate. So then all the delays, total delays, addition of all the delays, sum of all the delays, and it is again coming out in this form: G1 C out by C out 1 by C in 1 dash dash dash, isn't? Plus sigma of p, isn't? Now this sigma of p is not n into p. Okay, but it's a constant. Okay, for a given n, it's a constant. So now what is the product of all these terms? C out by C in n into C in n by C in n minus 1. Again, it's a constant. C out by C in 1. C in 1 is fixed from the previous circuit, the maximum load that previous circuit can drive. C out is fixed. Okay, so and into pi g. Now pi g is also term. It's pi g in inverter case was 1, but now it's not 1. It would be 4 by 3 into 5 by 3 into 1 into 4, something like that, isn't? So but the logic circuit, it's all the logic gates are fixed. You cannot change the logic gates, isn't? Because then the logic implementation would be changed. So that is unchangeable. So, and number of stages is fixed now. So pi g would be fixed. Pi g would not change. So pi g is capital G here. H is capital H is C out by C in 1. So that capital H into capital G is now fixed. Okay, and so pi G is fixed, capital H is also fixed, and pi G into capital H, that is capital G into capital H is also fixed. So product of all these terms is pi G into C out by C in 1, that is capital G into capital H is the product of all these terms, that is fixed, and sum of all these terms must be minimized. So again we come to the same point that all the terms must be equal valued using the same theorem as earlier, isn't? All the terms must be equal valued. So what do we again get? We again get a similar equation. So this capital P is now sigma of all the P's, okay, and capital G is pi of all the G's, and capital H is product of all the H's, isn't? Yeah. So we want to then now delay is, so right, I'm sorry. So what do we get again? Again we get that all the terms must be made equal, that is individual G into H, individual gates G into H, that is G into C out by C in of individual gate must be equal to capital G into H to the power 1 by n. Isn't? Here it must be made equal to capital G into H to the power 1 by n, isn't? Because this is the product of all terms, and so all the terms must be equal, means product of all terms is each term to the power n, isn't? So total to the power 1 by n is each term, isn't? Each G into H is capital G into H to the power 1 by n. Is that fine? I think this makes sense, isn't? So now this is the total delay. N is the fixed value of n that we had, to the power f is G into H, capital G into capital H is capital F to the power 1 by n plus pi of all the, okay. So there would be, in this logic part, there would be some inverters and some would be non-inverters. So sigma of all the inverters into n into my capital N is total number of gates minus inverters into P inverter. That is just a detail. It's the total number of total parasitic delays. So I have divided it into two parts. One is other logic gates, sum of other logic gates parasitic delay, and sum of inverter parasitic delay. So if there are capital N logic gates and N1 inverters in the logic path, then capital N minus N1 into, okay, I'm sorry, N1 is the logic gates, other logic gates, and capital N is total number of stages. So capital N minus N1 into P inverter, okay, plus 1 to N1 into logic gates, each logic gate, ith logic gates parasitic delay, okay, plus n into f to the power n 1 by n. Is that fine? So now I want to again find out the, when, for what n is it 0. So if I find that out, I again get similar expression, f to the power 1 by n natural logarithm of f to the power 1 by n plus f to the power 1 by n plus p inverter, because this becomes 0. This is fixed. Other logic gates you cannot change them. So what can you change? How can we change n? By adding or subtracting inverters. Because when you add inverters into the logic path at the end, suppose you are allowed to add inverters. So if you add inverters at the end, you are not changing the logic function. You may at best be inverting, but you are not changing the logic function. The logic function is there. It's preserving its form. Okay, if it was a plus b plus n or something, then it remains the same. The logic function doesn't change. By adding inverters, it can only get inverted. Okay, so suppose you are allowed to add inverters and thus optimize n. Till now we were saying that for a given n, what is the delay? So for that, equate G into H at each stage. That is the verdict that we have got. Now I am saying that I am allowed to add inverters also and find out an optimum n. So for that, again the equation would change only this way, because inverter doesn't change my pi g, and H also, capital H also doesn't change by adding inverter, because output capacitance is fixed, maximum input capacitance is fixed. So capital H into G doesn't change by adding inverters. Okay. So capital F doesn't change at all by adding inverters. Okay. So all my earlier, by adding inverters also, all my earlier conclusions are valid for a given n. I just want to find out how many inverters can I add, optimum. So if I find out optimum n, this in that n1 is the other logic gates which cannot be changed. So if I find out optimum n, actually I am finding out optimum n minus n1, which is optimum number of inverters to be added at the end. That is what I am going to find out. So that I find out by finding this, equating this to 0. Okay, so I get again the same equation as earlier. So again the same row, so again the same thing should be valid. Okay, so row is the same. I find the ideal number of stages, that is ideal capital N, is again found out in the same way. So once I find the ideal capital N, I already know N1. I know how many inverters can I add at the end. Okay, and then how do I size them? In the same way. I'll come to that later. But first question is, how do I reduce delay by adding inverters? That is a very paradoxical thing that's happening, isn't? Yeah. So that I'll try to answer. See, in a logic path, by adding inverter, what are you doing? You are reducing C out by C in of each logic stage. Yeah. So what is the value of G into H of each logic gate? It is total G into H to the power 1 by n. So when you add inverter, you are actually, when you add an inverter, this total G into H is constant. G is not changed, H is not changed. C out by C in 1 is not changed, H is not changed by adding inverter, isn't? G is not changed. Inverter to pi G inverter just contributes 1. So G is not changed. So G into H is constant, isn't? So by adding inverter, you are increasing N. So you are actually reducing G into H of individual stage, isn't? So individual stage G into H you are reducing. So G is the same. So you are reducing H of individual stage. So delay of individual stage you are reducing, and number of stages you are increasing. So delay of individual stage you are reducing, number of stages you are increasing. So you don't know where is the optimum. By increasing number of stages, you are increasing delay. By reducing delay of each stage, that is C out by C in of each stage, you are reducing delay. So it's going both the ways. You need to find out an optimum, and that's what you have done. Is that fine? Is that fine? That's what you have done here. Why is this optimum? So there is an optimum. It's not that by adding inverters at the end you will reduce delay. You may reduce delay. You want to find that out. Sometimes it may happen that the optimum n that you get through all this exercise is smaller than n1, is larger than n1. I'm sorry, it's smaller than n1. Then there is no point. You cannot change the logic. Then you just need to do G into H in the existing logic, whatever is the G into H to the power 1 by whatever is the already fixed n, and that is equal to the that to the power 1 by n is the individual G into H, and individual G you know. So from individual H you can size. Okay. So but if the optimum n comes out to be larger than n1, then you add inverters at the edge. Then how do you size? You know C out divided by rho is the input capacitance of last inverter. Likewise you go to this inverter which you have added, and then suppose you have an AND gate here. So the input capacitance of this inverter divided by rho into that divided by so that divided by rho into G. Now, see, for the NAND gate, rho consists of G into C out by C in. I want to find out C in of NAND gate. So G into C out by C in of NAND gate into C in of NAND gate is the input capacitance of this. That input capacitance divided by G into C out by C in, isn't? Then I have to multiply, that is the input capacitance of this inverter, that is straightforward. Input capacitance of this inverter divided by this ideal value of rho into the logical effort of NAND gate. That I have to do. Then I will get the size of NAND gate. Likewise, I have to go backward till the first stage. Is that fine? Okay, that's how I size the logic data path. Okay. And why do I need to size all this? Because this will define my clock period. Data path's maximum delay would define the clock period. That's why. Okay, so I want to have the minimum clock period possible. Okay, so this is where I'll end today, and I think we have completed at least without branching. If there is a logic path, how do we size individual transistors? A methodology for that. This methodology is called method of logical effort, and we have done a small part of it. It's an introduction. So this can also be used for variability, handling variability, etc., etc. It can be used for several other things. So that we have not discussed today. We can.
So we can go ahead with our query part in very quick session, and as we have to start our valedictory session at sharp 2. So please go ahead with your questions. If you have any question, please go ahead. Any query from any other nodal center, please? Is there any query from any nodal center? है कोई? Okay, if there is no query from any center, then I think we can end up. Yeah, please go ahead.
Sir, in the beginning of the presentation, we used the symbol alpha. So alpha is the proportionality factor, or can you elaborate on the term alpha used in the beginning of the?
Okay. It's not proportional. I was just saying that. Welcome. If I increase the input transition time by a factor alpha, I am also increasing the total output capacitance by the same factor. That's all. It's not a. It's just a factor by which I am saying that total output capacitance and input transition time, I am keeping them proportional to each other. I am not changing their proportion. So if I am increasing one by factor alpha, the other one also is being increased by the same factor alpha.
Any other query?
Sir, I'm from VLSI. I want to ask that there was a graph between delay and CP plus C outside WN. I have two questions. That this WN is actually the bit of the inverter or the NMOS?
NMOS. WN is NMOS, but WP by WN is kept fixed. So WN characterizes the inverter size.
And my other question is that CP by WN is basically the line that is parallel to delay line, or it is just a point?
No, it's a point on the x-axis. And there I again draw the delay line or y-axis.
So next question, please.
So in the graph, we showed it in a line that was parallel to the delay.
No. I'm saying that I'm shifting the y-axis, which is delay axis, by this much, Cp by Wn. That's all.
So actually, when we were talking about the graph between CP plus C also divided by WN versus delay. So CP upon C WN was the line which was shown parallel to the delay line.
No, CP upon WN is a point on the x-axis. X-axis.
The point of axis is the parasitic delay.
It's a point on the x-axis. No, it was not parasitic delay. Parasitic delay is a point on the y-axis. You can see. So if the slides can again be shown.
Slides can
Yeah. See, CP by WN is a point on the x-axis. And parasitic delay is a point on the y-axis.
So that is the point actually that was shown as a line which was parallel to delay line.
No. See, this is delay y-axis. I am shifting the y-axis by CP by WN on the x-axis. Okay. So this straight line now cuts the y-axis at this point, which I call parasitic delay.
So it means the axis was shifted towards the right side.
Right.
Thank you.
Thank you. Any other query?
Excuse me, sir.
Yeah, please go ahead.
I'm very confused.
Yeah, you are audible. Please go ahead with your query.
Yeah.
Yes, go ahead with your question, please. You are not audible. Actually, your voice is not clear. Please repeat your question.
What are the limitations of logical effect method?
Logical.
And the whole entire method.
Okay.
See, limitations. See, you need to first fix so many things. You need to see. It's not very accurate if your value of TR out, I mean output transition time, input transition time, ratios being equal, and all these conditions, if they are not fulfilled properly, the method is not very accurate. But nevertheless, it is sufficiently accurate to give you good good information about what sizes to keep for the transistors. So otherwise, everything gets dependent on post layout, extraction, simulation, redoing lot of simulations, trial and error. So to avoid all that, to get to the first point, to reduce the trial and error by a significant amount, this method of logical effort is a good method. One thing. The other thing is, if you can accurately maintain TR out by T in and TR in, etc., then it's very accurate. It's a very accurate estimation of delay. Then you can use it for other things. If you want to use it in a very accurate manner, etc., then you can actually use it in. See, it's very accurate if TR out by TR in is maintained. So that idea you can use in variability analysis. That's a different question. But for design, it would give you accuracy within say 10-15%, which is good enough for reducing the iterations in design. Okay. And if you do back of the envelope kind of estimations, that is 4 by 3 is the logical effort of NAND gate and all this, then it would give around 15-20% accuracy. If you find out the logical efforts from delay versus C out by C in plots, then it would give you a better accuracy. I could not understand what you are saying. Please repeat. Yeah.
Yeah, please go ahead.
Hello.
Yes.
So my question is, we have calculated some optimum value of n minimizing the d. So
Yeah.
in that we have for d, del of d by dl equals to 0.
Yeah.
I have confusion in line number third of that derivation.
Just let me see. Here.
So in that slide, we are calculating this.
So if you can show the slide.
Can you elaborate?
I will first show the slide. This slide?
The third line of the bill. Rho 1 minus ln rho.
Okay, just forget about rho. Just write it as f. F into 1 minus natural logarithm of f plus p. See, h to the power 1 by n. H to the power 1 by n is f, isn't? So this n you take here. See, n into 1 by n square. So you have a 1 by n left here. You have a 1 by n left here. 1 by n into natural logarithm of h. What is that? Natural logarithm of h to the power 1 by n. H to the power 1 by n is f itself. This f, isn't? So you have f minus f natural logarithm of f plus p. That f I am writing as rho due to some other reason. Rho into 1 minus natural logarithm of rho plus p. This rho and f are interchangeable. You take it that way. Then I think you will understand. Okay, I should not have changed the symbol here within the same derivation. That has caused the confusion.
So
This ln h is in the logarithm of h, and but 1 upon n is not a logarithm.
Huh? No, 1 upon n into logarithm of h is what? Logarithm of h to the power 1 upon n.
So that is part of logarithm, 1 upon n square.
No. 1 upon n square is outside. That's why this n and this denominator n square get cancelled. So 1 upon n into logarithm of h is equal to logarithm of h to the power 1 by n.
And that is equal to
Rho is h to the power 1 by n. Rho or f. Rho is equal to f. F is h to the power 1 by n.
so I think
Is that fine?
your query is now it is clear to you. And if any question is there, then you can ask. Otherwise, we can go ahead with our closing session.
the logarithm of h upon n is equal to logarithm of rho. Is it true or false?
Yeah.
Okay, thank you, sir.
Okay. With this, I think we can end up this session.
Yes.
So, please. We are really thankful to Dr. Anand Bulusho, who has given us this valuable time, and he just came here from IIT Roorkee at our institute to deliver these two excellent sessions, and he has opened door for all the researchers in so many areas. So you can have hint from his sessions, and then you can proceed with your research part. So it is really it gives us immense pleasure to you to be here, sir, with us, and you always give us time whenever it is required. We are really thankful for your cooperation, and I hope your session was really useful for our student as well as for our participants at different nodal centers. So we are going to now end up this session here only, and I request all the local coordinators at different nodal centers to please be ready at 2 sharp. We are going to start our valedictory session at 2, and our director is here with us today, and he is going to join us in our valedictory session. So time is fixed, it is at 2, because he has some other meeting after that this valedictory session. So my request to all the local coordinators are that be ready at 2 with all the participants at your center. So we will start our valedictory session at 2. Thank you. All right, please.
ये लॉक कर दे चाबी अपने हेलो ठीक है चाबी लॉक करके चाबी रख बाई चांस 10-5 मिनट लेट हो गए तो यार वो आ जाऊंगा 5-10 मिनट लेट होगा कितनी मिनट बता क्या क्या कर
Ravi?
अरे हटाना, ये हटा दो,
क्या
हटा दो ये।
क्यों
क्यों हटाना है?
इसको रिजेक्ट ही कर दो।
माइक म्यूट कर दो पहले।
शुरू हो गया भैया।
माइक अनम्यूट कर।
सर आप एक बार ना अनाउंस कर दो कि
Good afternoon, everyone. Within 5 minutes, we are going to start with our valedictory session. So all the local coordinators are requested to kindly be there and inform all the participants to be there in your center. Thank you.
मैं बैठूं।
I once again request all the local coordinators at different nodal centers, please be there and inform all the participants to be there in your center. We are going to start with our valedictory session within 5 minutes.
डी दो है। जी ये कितनी आईडी बनाई है इसकी? इसकी कितनी आईडी बनाई है? ये 15 सेंटर का कितने चैनल बनाए? कोई बनाए? ज़्यादा करता है। इसलिए सही है। वीडियो चलता नहीं है ना? इस पे पीआईपी भी होगी। टिकट यहाँ से टिकट पे कैसे कनेक्ट करेंगे? इस पे भी लाइन डायरेक्ट पे रखी है। बेसनल वाली। चेक इस पे थी कैसे? नहीं वो नहीं वहाँ से हमने दो निकाले।
इसमें पीएलपी सही हो रही थी।
कनेक्टेड है सारे बोलना कितने कनेक्टेड है? डिस्कनेक्ट कितने चले जाते हैं क्या? 90 कनेक्टेड है।
बाकी तो रिप्लेस सेंड कर
इनके कंट्रोल इधर से नहीं है। नहीं ये कैसे इधर से नीचे नहीं आते थे हमारे पास वॉइस कंट्रोल। ये वॉइस कंट्रोल ही नहीं आते ये तो इसके भी ये कहाँ है? वही कह रहा हूँ जैसे हम ये आई नहीं एक दो गए वही इस बार नीचे आएंगे एक बार ये सबके एक्सटर्नल ये इंटरनल यूज कर
तो वो उन्होंने एक्चुअली ऐसे ही मोहाली जाना था। अच्छा। तो अभी बस 2:30 बजे वहाँ से जाना।
आपके पास कोई बैठे हुए हैं? आप चलो ना। मेरे को पता है ना न्यूज़ स्टूडियो।
हाँ। नीचे वाला स्टूडियो तो चली नहीं रहा। या किसी को खड़ा कर देते हैं बाहर कोई स्टूडेंट को भेज देते हैं।
12 ये यूजर लिखना पड़ता है यार भाई लो लिखना पड़ता है अरे पिन वाला पिन वाला ले आओ ना उसको 3 बजे जाना
तो फाइनली 16 24 हो गया था
चॉइस पे कनेक्ट कर पा रहे हो आपको कोई दिक्कत नहीं।
सर वो जो गूगल एप्स ठीक था नीचे मतलब शुरू नहीं करवाया था सर जैसे वो 15 हो जाते हैं जो पेड वाले में तो वो मैंने नीचे एक्सपेरिमेंट किया था वो हो गया था मैंने एक पे
15 तो 2 पे कर लिए क्या वापस तो 30 हो सकते हैं
सर 30 नहीं 3 या 4 कम मतलब 26 क्योंकि सर शेयर करने के लिए चाहिए होता है ना
हमें फर्क तो नहीं पड़ रहा जैसे बात हो रही थी जैसे
पहले था ना दिक्कत
मैम जब बीच में जब बीएसएनएल की स्पीड कम हो जाती तब थोड़ा फर्क
इस प्रोग्राम में वैसे किसी का ऐसा फीडबैक आया नहीं कहीं एक आधे में अगर हुआ होगा
16 या 17 हमने कनेक्ट किया था तो फर्स्ट डे जब इनॉग्रेशन हुआ था तो फिर तो तुलसी मैडम थे तो it was perfect.
मैं उस दिन ना एक अकाउंट था हमारे पास, तो नेक्स्ट डे मैंने और अकाउंट क्रिएट करवा लिया था।
बाकी सर नीचे भी इस बार कोई कह रहे ठीक तो तुला मैम का कोर्स
अच्छा ठीक है,
6 सेंटर्स
अच्छा वो भी आज ही क्लोज हो रहेगा।
हाँ जी सर, वो हो गया
ठीक से, सबका फीडबैक ठीक है।
This interactive session.
अच्छा चलो ठीक है जी, प्लीज स्टार्ट। और एक से अपनी पूछना चाहेंगे कि कैसा लगा।
सिंगल सिंगल लेके चलें सर, एक एक को इनवाइट कर लेंगे फीडबैक के लिए, विद इन 1 or 2 minutes दे कैन गिव देयर फीडबैक। Respected Dr. MP Punia, Director NITTTR Chandigarh, respected Maitri Datta, Dr. Maitri Datta, Head Electronics and Communication Department, dignitaries, local coordinators, participants at different nodal centers, a very good afternoon to all of you. We are now at the end of this complete program. We are going to start with our valedictory session now. Let me brief about this complete 1 week program. Actually, in this program, total number of 24 nodal centers were connected, and out of those 24 nodal centers, 22 were engineering colleges and 2 were universities. And these nodal centers were from different states like from Rajasthan, Haryana, and then UP, Uttarakhand, Delhi. 3 centers were from Delhi. So total number of 24 centers were connected, and in these 24 centers there were 954 participants in all these centers. So in this program 954 participants were connected with us to participate in this program. Actually this program was a combination of both practical input as well as theoretical input. So in order to give this theoretical input, experts from different academic institutes were invited, and for practical exposure different experts from different industries were there. And academic institute include IIT Roorkee, IIT Ropar, NIT Kurukshetra, NIT Hamirpur. They were here to give their expert talks in different areas. Then we had expert from SCL Mohali, Cadre Design New Delhi, and TUPEL Technologies. They also gave their exposure in different softwares. So basically it was combination of both theory and practical, and 60% of the part was theoretical and 40% was industry oriented. I hope it was satisfactorily for all the participants of different nodal centers. If there was any problem at any time, if there was any problem, then all these lectures are there on YouTube. If you have missed any session due to some reason, you can watch those sessions in YouTube. Now without wasting much time, I am going to proceed with the feedback part. Now we would like to receive feedback from all the centers, and I request all the centers to please give us your brief feedback within 1 or 2 minutes, so that we can improve this program in future. So what are the things you think that we can improve, so that we can make this program more fruitful, more useful to our participants in future. So I will invite all the nodal centers one by one. So I request all of them to kindly please go ahead with your feedback, and be brief. Please complete it within 1 or 2 minutes. So first of all, I would like to invite ABS Ghaziabad. Yes, please go ahead. Your mic is not on. ABS Ghaziabad, please. Yeah.
This is Amit from ABS Ghaziabad.
Yeah, please.
I would like to express my vote of thanks to you regarding the program. The program is very helpful for all the faculty members, those who have joined for us, and they have learned some new technologies. And the speakers, those who have given their overall sessions that they have delivered, was very fruitful for them. I think that they will going to help it in their academic sessions. They can include those things in academic sessions, so that students also can get benefited from this. This is all from ABS Ghaziabad, sir. Thank you.
Thank you, ABS Ghaziabad. Next, I invite JSS Noida.
से क्लिक कर दोगे तो म्यूट हो जाएगा।
JSS Noida, please. JSS Noida, we are waiting for your feedback. Please go ahead with it.
Yeah, I'm Professor Prasad from JSS Noida. Good afternoon to you.
Good afternoon.
Can you hear?
Yeah, you are audible. Please go ahead.
We will just give you the feedback which we have got from the participants. My colleague Dr. Shazali is using details.
Hello.
Yeah, please.
Hello.
Yeah, ma'am, please go ahead.
Sir, the program was very good. It was very efficient and very learning for all the candidates.
Yeah, please go ahead.
So that was very informative and we
You-
see the info. The analog and digital design covered very nicely. And all advanced trends in technology, the current trends, they were covered very nicely by industry people. So altogether the program was very informative and thank you.
Any suggestion from your side? JSS Noida, any suggestion or means it was okay for you?
Hands-on say can be improved. Who can improve and so on. The content can be more on hands-on session.
Right.
And quality of
It was
audio and video.
60% theoretical, but can be.
And what about the quality of video and audio from our end? Video and audio quality was okay at your end?
Yes, it was okay here.
Yeah.
So one more thing to add that the sessions were going on. It was theoretical, but at times we felt the need of some software to be described, taken in more detail, in more one thing, because it cannot be covered and full knowledge cannot be gained in one session. Or you can focus on any one particular thing.
Okay, right. Thank you.
Thank you.
Next, I invite MMU University, Gorakhpur.
Good afternoon, sir.
Good afternoon.
I am Dr. R.K. Chaman from MMUT Gorakhpur. In all, we were having around 47 participants at this center. And the sessions that were conducted during the last 5 days of this week was excellent from most of the speakers. The only suggestion that we get, the only input that we get from our faculty members was related to that the fundamentals that were covered related to VLSI were repeated by 3-4 speakers, so that could have been avoided. Fundamentals of what is VLSI, what is IC, and how the development took place in the last 4 decades. So this was repeated by 3-4 speakers, so that could have been avoided by prior discussion. And the faculty members were more interested for some research output of these speakers also. Because of the paucity of time, they could not explain at the end what they have done at their end. But overall, the content that were presented by the speaker was excellent, and everyone is satisfied here. Okay, thank you, sir.
Thank you. Your point is noted here. We will take care of this thing in future courses. Next is Rewari Institute of Technology, Haryana. RKGIT, Ghaziabad. RKGIT, Ghaziabad, please go ahead with your feedback. I think they are not connected. Maybe. Yeah. Mic. Please make your mic on. It is on. Okay, go ahead. You can give your feedback. Okay, then we can move to the next one. Aryabhat College of Engineering, Ajmer.
सर आपका माइक ऑन है, आप बोल सकते हैं. RKG IT.
Hello, sir.
Yeah, please.
Good afternoon, sir. This session is the first session with you, and it's very useful. And the fundamentals of VLSI is very clear to our faculty members plus our students also get benefit of this online session. And by you.
Okay, you are from RKGIT or Aryabhat College of Engineering? Okay.
College of Engineering.
Okay, fine. All right, thanks. Next is JECRC Jaipur. JECRC Jaipur, yeah, please.
Good afternoon, sir.
Good afternoon.
So we are very much thankful for you to organize this workshop for the faculties of the ACRC along with many other institutes, and we are very glad that we attended this workshop. And the few features that you asked is the demo tools which you provided on your videos
Yeah.
are very good, and especially the session on visual CAD, that was excellent, and everybody was interested in attending that. And along with that, sir, there is one more query, base queries, and first query is, can you provide us a direct link to the NITTR website for these videos instead of searching them on YouTube?
Yes, at present these videos are available on YouTube, and maybe after some time these videos will be also available on what is the link?
नई चैनल क्रिएट की ना, अलग नया चैनल बन गया, उसमें VLSI नाल साथ में डेट डाल देंगे ना तो वो निकल आएगा.
Okay, if you want to view any of one of these sessions, you can just explore by just typing VLSI design and with date, because earlier we also conducted 2 more programs. You have to write down VLSI design program and day 1, then you have to just enter the date of that one. Then you can have that complete session of that complete day, right?
Yes, sir. And one more question to ask. Can you visit JECRC, I mean, for providing particular lectures, like guest lectures?
Repeat your question, please.
Can you visit JECRC, I mean, like instead of video lectures, can you send someone for the...
Okay, you means contact mode program.
Okay, so thank you.
Right. If you are interested in contact mode program, then you can talk later on. We can have that also, right? Yeah, that is also possible. There is no problem. So next I invite HITM Agra. HITM Agra, please. I think they are also not connected at present, so they are connected. HITM Agra, can you hear us? Okay, we will come back shortly after this one. Okay, Khalsa College of Engineering and Technology, Amritsar. Yeah, please.
Hello.
Yeah, please go ahead. Good afternoon. Good afternoon.
Thanks to you for Khalsa College of Engineering and Technology. First of all, I congratulate Dr. Videsh Mehra for successful conduction of this VLSI course. It is very interesting and knowledgeable.
we are first time let this type of course in our institute, and as far as experts are concerned, the experts are very good and knowledgeable, especially the lecture by Dr. Rohit Sharma from IIT Rohtak, Dr. Nan from IIT Roorkee is very good and knowledgeable. Thank you very much.
Thanks. Now I invite DIT University, DIT University Dehradun. DIT Dehradun. Disconnected. Next I invite Institute of Engineering and Technology, Dr. B.R. Ambedkar Institute of Engineering and Technology, Professor Amit Singhal. Next is JCDM College of Engineering, Sirsa, Haryana.
Hello.
Hello.
Yeah. Good afternoon, sir.
Good afternoon.
So, first of all, I would like to thank Dr. Puneet. The policy part that I want to discuss with our today's discussion, that is the designing and the history of from the designing part of view in the VLSI design. The content was fabulous. I must congratulate the NITTTR team. The content part was really very good, and this is up to the mark, and 100% all the faculty and all the students who have attended this workshop, they 100% find the good content part. The suggestion part, I would like to say a few things. First of all, the size of the text in the PPT, sometimes it is not visible. I mean, the presenter may have looked this the size part, but sometimes because we are seeing in the projector part, sometimes text is not visible. So next time when the text is concerned, size of the concern must be 28 or something, 26 as it may be.
Yes, PPTs.
The second thing, sir, if it is possible, the hands-on practice or some interactive lab sessions, if it is possible, something can be done, because we are just seeing something, but we are not able to actually conceptualizing the things until unless we are not doing the things by our hand only. So if जरूरी नहीं है कि हम सारा wide range must be there. Some small content could be small, but it should be some real part should be there. Because everything seems to be very virtual. If hands-on session will be there, so it will be more more understanding part ज़्यादा हो सकता था और थोड़ा अच्छा हो सकता था. So these are the few suggestions that from our side.
Okay. Yeah. So just let me tell you one thing. Actually, this same suggestion is coming from second center about this hands-on practice. Actually, as you know, there were 24 centers connected with us, and if we start basically this practical exposure from this side, it is very difficult to synchronize all the 24 centers at once. So that is why there may be very big problem in making synchronization in different centers. So otherwise, whenever we run these type of courses in our institute and we concentrate on hands-on experience practicals only, you can do that thing. But still, your point is very well noted down. We will try to work on it, and if we can do something, then we will try to do it. Right. So thank you very much. Next, I invite Gyan Jyoti Group of Institutions, Professor Neeraj Sharma.
Good afternoon, sir.
Good afternoon.
So we thank all from NITTTR to give us this opportunity to be a part of this event. We thank Dr. Rajesh sir and the whole team for coordinating this informative event for us. Session by Dr. Rohit on high-speed interconnects and session by Dr. ER Amit Saini on 3D device modeling were all innovative and learning based. So we all thank you for this learning experience. It was a good session for us.
Thank you. Now I invite NC College of Engineering, Panipat.
Hello.
Yes, please go ahead. Yeah, good afternoon.
Myself Ajay Jaswal from NC College, EC department.
Yeah, please go ahead.
Hello, we have a 5-day workshop based on VLSI design that was very interesting and almost topic like analog CMOS design, Verilog based FPGA and CMOS design or digital CMOS design. That was very interesting, and also that topic related to MTech flavors and BTech familiar flavors. And I say thankful to you, NITTTR Chandigarh, recognized first interactive workshop from the faculty of PC, for the faculty of PC. Thank you, sir.
Thank you. Now I invite ICLIET Ambala. अभी कंप्लीट कर लेते हैं फिर बैग आएंगे. ICLIT Ambala. Then I will move to the next one, AIT Tonk, Rajasthan. AIT Tonk. मेवात इंजीनियरिंग कॉलेज, हरियाणा. मेवात इंजीनियरिंग कॉलेज, हरियाणा. MIT मुरादाबाद.
Good afternoon, sir. Good afternoon. Sir, I should have message about the problems we had faced. First is the audio quality during query sessions. It become an echo sound and we will not able to listen the question that has been asked. It become echoed, sir.
Okay.
First thing. And
you are from MIT Muradabad?
MIT Muradabad, sir.
Okay, fine.
The questions that the queries arises, it is not listenable because of the echo. I hope so. Right?
Okay, echo problem was there.
Yes, sir. Secondly, I should that the schedule should be followed strictly, sir, because the academic session is going on. We have had the classes as well as all other assignments.
Right.
And third, sir, I should propose that one session of single day should be total hands-on training. We should be available with the software in our laptop and let's have some discussions and training sessions totally on software, sir. There are 3 different sessions of a very short duration. If it may possible for a full day, it will be beneficial to us, sir.
Okay, right. So, we can include that one also. There is one more problem in that. Whatever exposure was given to you in this whole program, one software was from Cadence. It is licensed software and its cost is around 24-5 lakhs. Means this software is not available at all centers. TCAD software is also it is around 6 to 10 lakhs cost. It is also licensed version. It is not freely available on the net. So that is the main problem. It can be done if all the centers have that same software. Basically, here we give the start. So these are the softwares available. If you are interested in your research by using these softwares, then you can proceed further. So this is also one problem. So that same software should be there at your end also.
Thank you, sir. Thank you.
Right.
And last request, sir, certificate should be made available early, sir.
Yeah, definitely. Sure.
And overall, sir, overall experience is very good.
Yes.
And we should hope so that we will again be part of this course, sir. Thank you.
Right, right. So whenever you are going to send us the complete detail of your list of participants, certificates will be dispatched after that from here.
Okay, so I had already made its 41 number of participants.
Okay, okay, good. Thank you. And then Universal Polytechnic College, Lalru. Universal Polytechnic College, Lalru. Is it connected or? Please switch on your mic. Switch on your mic and please go ahead with your feedback. Now I invite GT Delhi for their feedback.
Hello, good afternoon, sir.
Good afternoon.
Myself, Dr. Maneet Singh from Guru Tegh Bahadur Institute of Technology, and I am highly thankful to the coordinator, sir, Professor Mehra, and head of the department. It was a very nice and the VLSI design course was very excellent. Here the sound quality is very excellent. I am also thankful to our management who is also present here, our chairman, Sardar Avtar Singh ji, manager, he is also present, Shri Vicky Manji, and directors. They are also the part of this for attending the valedictory ceremony, sir. So on behalf of them also, I am highly thankful for being us the part of this course. Now our director, madam, she would also like to say a few words regarding this course, sir. Thank you.
Yeah, please.
A very good afternoon to all of you. First of all, I extend my heartiest thanks to NITTR Chandigarh, especially Professor Punia ji, who has organized this program in our institution, and our faculty members who are all sitting here. Our management is there, our chairman, Professor Sardar Avtar Singh Hichi is here, Sardar Vicky Manji is here, our HODs, all faculty members are here, and all of them are feeling very happy and excited. They are benefited by this program, and they are able to learn a lot about this VLSI design, and the sound quality is also good, and it can further be improved. That is one of the suggestions from our side, and we look forward to many more such training programs for faculty members. These are highly useful, and even we have invited faculty from other institutions, nearby institutions of our area. So I thank especially Dr. Rajesh Mehra ji, who is the coordinator of this program, for organizing this program in our institute, and we will be looking forward to more such programs in our institute. We thank you all, and my management. Our management also joins me in thanking NITTR Chandigarh for this job. It is indeed a very great job to listen, expert advice from very highly reputed professors, accomplished professors who are able to share their experiences with our young faculty member, who will in turn be benefited by these guidance of these experts. So I thank you all for this program.
Thank you, ma'am. We invite and we welcome your chairman also in this valedictory session, and we will be happy if your chairman want to share his views with us.
ਮੈਨੂੰ ਇਸ ਗੱਲ ਦੀ ਬੜੀ ਖੁਸ਼ੀ ਹੋਈ ਆ ਚੰਡੀਗੜ੍ਹ ਤੋਂ ਸਾਡਾ ਸਟਾਫ ਸਾਡੀ ਫੈਕਲਟੀ ਤੋਂ ਟ੍ਰੇਨਿੰਗ ਲੈ ਰਹੀ ਆ ਬੜੀ ਮੈਂ ਤਾਂ ਪਹਿਲੀ ਵਾਰ ਦੇਖੀ ਹੈ ਲੇਕਿਨ ਬਹੁਤ ਹੀ ਅੱਛਾ ਹੈ ਤੁਸੀਂ ਜਦ ਸ਼ੁਰੂ ਕੀਤਾ ਬਾਕੀ ਕਾਲਜਾਂ ਵਾਲੇ ਵੀ ਸਾਰੇ ਲੈ ਰਹੇ ਪਰ ਮੇਰੇ ਕਾਲਜ ਵਿੱਚ ਇਸ ਗੱਲ ਦਾ ਮੇਰੀ ਫੈਕਲਟੀ ਤੇ ਬਹੁਤ ਅੱਛਾ ਅਸਰ ਪਿਆ ਖਾਸ ਕਰਕੇ ਸਾਡੇ ਤੇ ਪਿਆ ਸਰ ਕਿ ਜਿੱਥੇ ਵੀ ਕਿਤੇ ਕੋਈ ਕਮੀ ਪੇਸ਼ੀ ਆ ਉਹ ਵੀ ਦੂਰ ਹੋ ਸਕਦੀ ਆ ਅੱਗੇ ਨਵੇਂ ਤੋਂ ਨਵੇਂ ਕੋਰਸਾਂ ਵਾਸਤੇ ਹਰ ਗੱਲ ਦੀ ਨੂੰ ਠੀਕ ਸੁਲਝਾਉਣ ਵਾਸਤੇ ਬਹੁਤ ਅੱਛਾ ਉਪਰਾਲਾ ਕੀਤਾ ਮੈਂ ਸਮਝਦਾ ਬਹੁਤ ਵਧੀਆ ਵੈਰੀ ਗੁੱਡ ਆਈ ਵੈਰੀ ਹੈਪੀ ਯੂ ਆਰ ਐਫਰਟਸ कि विद्या विचारी तो परोपकारी जो विद्या ही ऐसी चीज है जो संसार में कभी खत्म नहीं होती हमेशा चलती रहती है, मरने के बाद भी ये जिंदा रहती है। जो लोग पीछे छोड़ जाते हैं किसी बात को, किसी चीज को छोड़ जाते हैं, वो जिंदा रहती है। आज हजारों साल बाद भी उनको याद करते हैं हम। इसलिए मैं आपको इस बात की बहुत बहुत मुबारकबाद देता हूँ। ये उपराला जो आपने किया है बहुत बढ़िया। आई एम वेरी हैप्पी ऑन योर।
थैंक यू वेरी मच जी आपके इन वर्ड्स के लिए। और इन नियर फ्यूचर आल्सो हम आपको एश्योर करते हैं कि आपके इंस्टीट्यूट्स को आप रेगुलरली हम कनेक्ट करेंगे हमारे सेंटर के साथ। थैंक्स वंस अगेन। नाउ आई इनवाइट इंदिरा गांधी दिल्ली टेक्निकल यूनिवर्सिटी फॉर वुमेन, दिल्ली।
Hello, sir.
Yes, please.
Yeah, good afternoon, sir.
Good afternoon.
It's a great honor to be a part of this program as a nodal center, and I take this opportunity to thank Dr. Rajesh Mehra, the authorities of NITTTR Chandigarh, the administration of IGTQW, and the IT services to make this program a successful event. Further, I would like to add that we had approximately 50 participants that cover the internal faculty members, faculty from Delhi University, IP University, Bharati Vidyapeeth College of Engineering, and certain colleges from the NCR. And it was a great opportunity for them from different diversified backgrounds to learn about the VLSI, and many of the faculty members, they are looking forward to merge VLSI with their signal processing or mechanical or other fields. So we would like to be a part of this kind of opportunities in the near future as well. Thank you, sir.
Thank you, madam. Sure. In our future courses also, we would like to connect your university in as our nodal center. Now I invite JECRC UDML, Jaipur. Your voice is coming here. Please go ahead with your feedback. JECRC UDML, your voice is coming. Please go ahead with your feedback.
Hello, hello. Are you able to hear me?
Yeah. Please go ahead.
Good afternoon.
Good afternoon.
All the participants were fortunate enough to have some of the renowned and eminent professors and speakers in this ICT-based training program on VLSI design. Most of the sessions had proper blend of theoretical and practical inclusions. This served as a wonderful platform for better understanding of the concepts. We have suggestions, sir.
Yeah, please.
Please refer to third session on day 2, that is 3D device modeling.
Okay.
It would have been a more learning experience of the software if we could have received that the software possibly its trial version before the training program and had installed it in our laptops and had practiced it with CAD design software personnel. Thank you once again for such a wonderful training program on VLSI design. Thank you, sir.
Thank you very much, and thanks for your suggestion. Yes, your suggestion is very valuable. They provide 1 month demo version of that software. So next time we will try to have that license version for all the centers, so that you can install that software at your centers, and then we can have hands-on experience on that software simultaneously. Thank you very much. Now. Next college is Northern India Engineering College from Delhi.
Sir, hello.
Yeah, please. Yeah. Go ahead, please.
So good afternoon, sir. First of all, I'd like to in person thank Dr. Rajesh Mehra for including our institute into this program, and on behalf of the faculty and the institute, again I wish to thank that all the sessions were very informative, and one of my questions that has been half answered was regarding the inclusion of lab sessions. In this context, as you have already said that it is not practically possible to include at a large scale, since there are around 24 to 25 institutes attached with you. But in this context, my request or suggestion is As far as the theory part is concerned, the sessions were elaborative, informative. Simultaneously, for example, in this context, VLSI, we have a tool on physical design. So maybe certain slides to facilitate and to encourage people, we can include some sessions to have or to deliver or transfer knowledge on behalf in this context as well.
Right, sure. In our next program, we will try to include this one. Any other suggestion from your side?
Thank you, sir. Thanks a lot, sir.
Thanks a lot. Now again, we will move to DIT University Dehradun. If they are connected, please go ahead with the feedback. DIT Dehradun. Actually, your mic is off. Kindly switch on your mic. DIT Dehradun, please switch on your mic. Your voice is not coming here. Professor Anuj Sharma.
सर हैंगआउट की स्क्रीन पे सेंटर टॉप में सेटिंग्स का बटन है, उस पर क्लिक करिए और माइक इनपुट चेंज करिए माइक की. मे बी आपने दूसरा माइक सिलेक्ट कर लिया जो इस समय इनेबल्ड नहीं है. गो टू सेंटर टॉप में सेटिंग्स बटन इन हैंगआउट विंडो, देन क्लिक ऑन माइक्रोफोन.
प्रोफेसर अनुज, अभी भी आपकी आवाज नहीं आ रही है. यहाँ पे आपका माइक जो है वो प्रॉपरली वर्क नहीं कर रहा है.
और सर यू कैन type your TeamViewer ID and password in the chat window so that we can make it correct.
Or you can give your comments in our command window. You just type your comments in command window, then we can have those comments from your side. You just type your comments. In between, we can now make this house open. If anyone is left for feedback, they are most welcome. Please, if any institute is left, they can go ahead with your feedback. AIT Tong. Please go ahead with your feedback. नहीं है मेरे ख्याल से. I think if no more institute is left for feedback, then we can proceed further in our this. This is AIT. ये तो AIT Tong है. Okay. Alright, we got your comment, DIT Dehradun. RKGIT Ghaziabad. Please go ahead with your feedback. RKGIT Ghaziabad. Yeah, please be loud. Go to your laptop and then you can give your feedback. Your voice is a bit slow.
Okay. I'm just going to type.
RKGIT, we are not able to hear you. You can go near to your laptop and then you can give your feedback.
Hello.
Yeah, please. Or you can be a bit loud.
Sir, your voice is not audible. Hello.
Yeah, please go ahead. Now we can listen you.
Okay, sir. Sir, this is Dr. Puneet Srivastava. This program is really beneficial. In fact, from our faculty members, 5 faculties are personally engaging in VLSI design. As per their feedback, they definitely get benefited by this type of program. And so, we are very thankful that you consider us as a nodal center. Thank you so much.
Thank you. Thank you very much.
Okay, thank you.
Right, thanks. RD Engineering College, Ghaziabad. RD Engineering College, your mic is not on. Please switch on your mic. So I think, yeah. Yeah, please. So I think we can go ahead with our valedictory session. Now we have received feedback from all the nodal centers, and some very good suggestions were. ICLIT Ambala. You want to give your feedback? Please go ahead. ICLIT Ambala. Please switch on your mic. Your mic is off. ILT Ambala, switch on your mic and then give your feedback. चलो ठीक. So I think our feedback part is now almost complete, and we have received some very good suggestions, and definitely we are going to work on those suggestions, and we will try to improve this program further next time. Now it is time. We have with us Dr. Maitri Datta, Head Electronics and Communication Department. Now I invite Dr. Maitri Datta to please share her views with us. Dr. Maitri Datta, please.
Good afternoon to all of you, and first of all I thank our director Dr. MP Punia for motivating us, and I congratulate Dr. Rajesh Mehra also that your hard work is visible with the centers. So many centers we are connected today with NITTTRCHD Chandigarh. There are 24 centers are connected in this course, and definitely the feedback comments from all the remote centers are well taken by us. Sir, I suppose this is the first time that our institute had connected with 24 centers, and nearly 1,000 participants are connected today with us.
So it is a very good achievement from our part, and I congratulate Rajesh for his hard work to connect, because it is not so easy, you know, to connect with so many centers, to coordinate with so many centers, and actually we have got so many good suggestions from all the remote centers, and definitely we will do our best to modify, you know, some things, for example, that hands-on experience. So Rajesh has given a good option that 1 month trial version we get with all this licensed software. So in next courses we will try to do that 1 month prior only we can give all the centers that who will be connected with us, that this 1 month trial version of the software, so that you can just load onto your laptop, and on the day of the hands-on experience you can bring those laptops and we can do that practical part. And definitely in our department I will say that we have very good established VLSI design lab, and here we have you know, the Cadence software, that Cadence industry, some people had come and had given some demo, or had given some introduction about the software we have already purchased. So if anyone from any centers, any remote centers, if anyone you are interested in learning this software, you are welcome to NITTTR Chandigarh, because we are conducting this type of courses in VLSI design and other courses in NITTTR Chandigarh also. And if you are interested to conduct the courses at your end, then also it is possible, but that time also some software issue comes, but that we can solve it, you know, with the communication with you, or some this trial version of the software, that we can do it. But definitely we can do the courses in contact mode at your organizations. And thank you all the participants for giving such nice feedback comments, because these feedback only, you know, motivate us to do again better in our near future courses. So this feedback evaluation and feedback, you know, this evaluation procedure and the feedback comments are very important in our part also, so that we can get some good suggestions and we can get the motivation. And again I congratulate Rajesh for your good work and hard work. And sir, definitely everything is possible for your motivation only, and I just thank from my heart that you have started these ICT based courses. And for this type of courses only, today within 5 days we could train near about 1,000 participants from all over India. That is a very good achievement from our part. Thank you, sir.
Very good, wonderful.
Thank you very much, ma'am, for your support and encouragement all the times. Now we have with us Dr. MP Punia, Director NITTTR Chandigarh, to grace the occasion. I request our director to kindly address the gathering.
Good afternoon, Professor Maitri Datta, Dr. Rajesh, my team members, dear friends at NITTTR Studio, participants at different centers. First of all, I'll extend my sincere thanks for supporting NITTTR Chandigarh, and special thanks to Professor Maitri Datta. What she is saying, how flexible we are. If you are interested to come for training, please do come to NITTTR Chandigarh. If you are not interested to come to NITTTR Chandigarh, we'll come to you. And even both are not possible, through ICT we'll be reaching to you. So how much flexible she is and how many opportunities she is extending, it's wonderful. And this attitude reflects that how serious her department is. I think in a government system and a teacher is giving 3 options, I think it's amazing. Particularly in India, the rigid system which we are having, or the type of unproductive work which we are having in our system, if someone is saying I'm having all the options for you, money is not the constraint, time is not the constraint, it's beyond imagination. Dr. Rajesh, you are so much in demand, that I can see. 24 centers, 1,000 teachers. In a year, one organization is conducting programs and imparting training to 1,000 teachers. Yesterday I was at I was at Bombay, and there is a center for instrumentation. It is Western Regional Instrumentation Center. It's UGC center, and crores of rupees they have spent on this one for imparting training on these instruments. In fact, for industry people, for teachers, for universities, they are having around 60 members in that center. Government of India is giving enough money to them, and in a year the number of persons who are being trained by those 60%, it is ranging between 400 to 500. Means in a year the output of 60 people is 400 to 500, and your department in your this thing coordinationship, if you are imparting training to 1000 teachers in a week, we can imagine that how productive you are and what is your vision. IIT Bombay has started one program. In a year they are conducting one program, and they are saying 100 centers we are connecting, and each center is carrying 100 teachers. Means they have planned for 10,000 teachers. I think your next target should be not 10,000 but 10,001. I want to beat IIT also. No, we are nowhere inferior from IIT. We are nowhere inferior to anyone. Even we are capable to connect centers at international level also. One program will be we are conducting in the month of Feb, when from all over the world centers will be connected. It is on sustainable business. In fact, sustainable business. Any entrepreneur who is entering for this entrepreneurship, how his or her business can be socially responsible and sustainable. So NITTTR Chandigarh is doing wonderful job, and your department, madam, is its very special effort. Some of the suggestions, even the feedback which we are receiving, it's very good. First of all, the quality of audio, video, I think there is more or less complaints have gone now. 2 years back when we started this type of program, contents were not able to discuss during this valedictory session. Only the complaints which were coming, that was audio video. Now there is no complaint related to audio video, even related to content there is no complaint. Only suggestions are coming that how this hands-on part can be improved, and that's very true also. Even this electronics, which are most promising branch in the country, most demanding branch in the country, at around 5 years, 6 years back, today institutes are facing a problem. Students are not getting attracted towards electronics branch. However, the demand in the market of electronics graduates are increasing, but as far as students entry into the institutes are concerned, that entry is declining. So it's a very serious issue, and one of the reason of that one, that our electronic graduates who are coming out, their hands-on part is weak. And particularly these subjects, VLSI design, which I am saying, it is assumed to be one of the toughest subject, or microelectronics, when I am saying, these are assumed to be very tough subject. So if these subjects can be made some easier or popular, or particularly interest can be created of the students, I think again students will be getting attracted into this electronics branch. And these tough subjects, if it can be made, even their performance will also be good, their academic results will be good. So more stress has to be given, as has been suggested by our centers. One of my suggestion is putting softwares at every center. It is very difficult because many of them are licensed software, lot of money is needed for that one. One thing which we can do, for these softwares which are rarely available, licensed software, can we create some of the videos, hands-on part here itself, where teacher is demonstrating every step of that software is explaining, and can we record here, say some of the suggestions we can take from our center. They'll be giving suggestions that related to this software, these steps has to be there, and these steps has to be explained properly. Then use of the software will be easier, and even if you are not having that software, at least that outer idea of that software will be having. So can we create some of the videos with the help of our centers or some of the experts which already you are invited, or for this purpose, for those contents of the software, even some of the experts which are available in the country can be invited here, and some of the good videos can be created, and those videos we can put on our web portal, where quality of sound, quality of video, everything will be good, and that will be available on our web portal. That we can do. Even we are inviting all the centers also. whatever expertise you are having, particularly in this area VLSI design, please do come. It may be hands-on part, it may be theoretical part. Please do come to NITTTR Chandigarh. We are having wonderful facilities here for the purpose of recording. We'll be recording your knowledge, we'll be putting on our web portal, so thousands, crores of lakhs of students of this country can be benefited, and we are paying handsome amount. When I'm saying handsome amount, means it is really handsome. Your stay, your travel, and for 1 hour lecture we are paying 5,000 rupees if you are getting recorded in our studio. So please do come, join hands with NITTTR Chandigarh. As madam is saying, we are having many options. In the same fashion, you please float many options also from your side. It will be factorial, our options multiplied by factorial your options. Thousands of options will be there, and certainly the quality of this education will improve, and that exactly we want. Through this program, we wanted to create some interest, we want to create one spark from our side. Now flame has to propagate. Yes, more interest from your side. Even some of your students may be doing MTech, thesis may be doing in VLSI, even some of them are doing PhD also. Please give your inputs, and if any help is needed from NITTTR Chandigarh side, please utilize our expertise. Even I can ensure you, if expertise is not available at NITTTR Chandigarh, we'll hire from any prominent institute of the country, and even if it is not available in the country, even we can hire from outside the country. That much autonomy we people are having, that much money we are having. Institute is not having dearth of the money, only initiation or proactive role from your side it has to be. NITTTR Chandigarh is very keen. We people are working hard, day and night we are working. Even people who are controlling, even people, the students who are managing this program, their efforts, you can't imagine that how much efforts these students are putting. Day and night they are working, and that's the reason, that's the outcome, that this ICT facility has become so effective. And at your end, no infrastructure is needed. Just you are having a laptop, you are having a dongle connectivity, you are having one LCD projector, that's all. Otherwise it was a Havva, that ICT, the having video conferencing equipments, cost, everything was too much. Nothing is there. Whatever cost is there, it is coming to NITTTR Chandigarh, not to your side. We have made the system so effective. Even madam has created another facility, that is through People Link. Whatever you are receiving now, it is through Google Hangout. Even parallel system we are having, it is another software we are using. It is software based only, not hardware based. So through People Link also it is becoming very effective. So both the efforts we are doing, both the mechanism we are using. At present in NITTTR Chandigarh, 6 studios are working parallelly. One studio is only for the purpose of recording, one studio from which this program we have delivered, another studio, it's just simply a classroom, where another program we have completed, 6 centers were connected there. Even our boardroom is a studio, even our communication skill lab is our studio, even your electronic service center is a studio, computer center is studio. More than 6 and these studios are working simultaneously, so 6-7 programs simultaneously we can conduct. Our web portal is carrying all the information related to our training programs. In a year, around 300 programs we are doing. 300 programs means in a year there are 50 weeks, means every week we are doing 6 programs. So please join hands with us, and in time to come we hope the deficiency of the teachers as well as their confidence level which we are having, it will improve by the efforts of the NITTTR Chandigarh. So again I am extending my sincere thanks to all the teachers who are connected, even from Guru Tegh Bahadur Institute, the chairman was there, the director principal was there. So I can assure you, we people are ready to extend any type of help, but the target is whatever knowledge we are gathering, it has to reach to our students. That's the foremost task. Even we can conduct some of the programs for students also. Many programs we are conducting for the students, particularly for improving their communication skills. So even you can join those programs also, and those programs are meant specifically for students also. One capsule program, one-day program we are conducting on your request for the students, how they have to appear in the interviews, how they should present themselves, how their CV has to be prepared, how they should participate in the group discussion. So according to their requirements, one capsule program we have devised. That capsule program also we can conduct according to your requirements. So thank you very much, best wishes, and Dr. Rajesh, please keep these efforts continue, and hope the target which are given to you for 10,001 teachers at one stage you will be able to achieve. Best wishes.
Thank you very much, sir, for your motivation, encouragement, and unconditional support every time. And we assure you, sir, we will try to achieve that target, whatever you have given to us. Now it is time to extend my vote of thanks to all the dignitaries present at various nodal centers, local coordinators, and then participants, our ETV staff, our ME and PhD students, and special thank to our director, Dr. MP Punia, for his unconditional support every time, and our head, Electronics and Communication Department, Dr. Maitri Datta. She is always ready to experiment new things. So it is really good, man. And this with this kind of motivation, we can do wonders. So once again, I am thankful to all the participants for their support and for their patience. Thanks a lot. Okay, if you have missed any videos, all the videos are available on our NITTTR site. You can open the YouTube site, that is www.youtube.com. There you can search ETV1 NITTTRCHD and new. You will get all the videos of this session on this channel. So I think if you have missed any session, you can enjoy that session from these videos. So these videos are already available on YouTube. Thank you very much.